The universe is full of mysteries, and the more we uncover, the more questions we seem to have. What is the invisible force that holds galaxies together? Why do some stars seem to defy the laws of physics? Join us as we embark on a quest to uncover the greatest unexplained mysteries in the universe. The axis of evil refers to an intriguing feature observed in the cosmic microwave background radiation, which is the afterglow of the Big Bang. It represents a peculiar alignment of large-scale structures in the universe that seems to point towards a specific direction in the sky. This phenomenon has sparked considerable debate and investigation among cosmologists trying to understand its implications. Typically, the cosmic microwave background radiation is expected to be uniformly distributed across the sky, reflecting the early universe's isotropic nature. However, some researchers have noted that certain anisotropies, or irregularities, in this background radiation appear to align with the orientation of our solar system and the Milky Way galaxy. This unexpected alignment has led to questions regarding its origins and whether it challenges existing cosmological models. One possibility is that this alignment might be a statistical anomaly, resulting from the limited volume of the universe we are capable of observing. Alternatively, it could indicate some underlying cosmic structure that we have yet to fully understand, perhaps hinting at influences beyond our immediate galaxy or the legacy of processes from the early universe. Despite extensive studies, the origin of the axis of evil remains open to interpretation. Some scientists argue it could simply be a product of observational biases, while others propose it may reveal new physics at work on cosmological scales. As technology advances and our observational capabilities improve, the quest to unravel this cosmic mystery continues, potentially transforming our understanding of the universe and its formation. The strange cold spot in the universe, formerly known as the cold spot, is a large area of the cosmic microwave background radiation that appears unusually cooler than surrounding regions. This anomaly, which spans about 10 degrees in the sky, has intrigued scientists since its discovery, raising questions about its origins and implications for our understanding of the cosmos. One theory suggests that the cold spot might be a byproduct of a supervoid, an expansive region in space with significantly fewer galaxies and matter than average. If the cold spot coincides with such a void, the reduced density could lead to less gravitational influence, which may cause the cosmic microwave background radiation to lose energy as it travels through this underpopulated area, resulting in a cooler temperature when it reaches us. Another possibility is that the cold spot could arise from fluctuations in the density of matter during the early universe. This theory aligns with current models of cosmic inflation, where rapid expansion could create areas of lower density and temperature. The patterns we observe could be remnants of quantum fluctuations that occurred shortly after the Big Bang, now manifested as this chilly region. Some scientists even entertain more exotic explanations, including the idea that the cold spot might reflect interactions with other universes, suggesting that our universe is just one of many in a larger multiverse. While these theories present fascinating possibilities, the true nature of the cold spot remains a mystery, drawing ongoing investigation as researchers explore what it might reveal about the fundamental aspects of our universe. Giant cosmic voids are vast, almost empty regions in the universe that contain far fewer galaxies than their surroundings. These voids can stretch across hundreds of millions of light-years and contribute to the large-scale structure of the cosmos. Understanding their formation requires delving into the processes that shape the universe since its inception. The prevailing theory involves the early universe's evolution following the Big Bang. During this period, matter was distributed relatively uniformly. However, tiny quantum fluctuations in density led to irregularities. As the universe expanded and cooled, gravity began to attract matter towards denser regions. Over time, this accumulation formed galaxies and clusters of galaxies, while the less dense areas evolved into voids. Cosmic evolution continues to influence these voids. As matter falls into denser regions, these voids can grow even larger. This process creates a web-like structure known as the cosmic web, characterized by filaments of galaxies surrounding the vast empty voids. This large-scale structure is fundamental to our understanding of how galaxies are distributed in the universe. Interestingly, voids are not entirely empty. They host some intergalactic matter and even a collection of dwarf galaxies. Studying these eerie cosmic voids helps astronomers gather insights into dark energy and the universe's overall expansion. The presence and dynamics of voids challenge our understanding of cosmic evolution and highlight the intricate and often surprising nature of the universe's architecture. The strange filaments connecting some galaxies are a fascinating aspect of the universe's large-scale structure, often referred to as the cosmic web. This cosmic web consists of a network of galaxies, clusters, and voids, with filaments serving as the bridges that link these dense regions of matter. Understanding the formation of these filaments reveals much about the evolution and dynamics of the universe. The formation of filaments can be traced back to the gravitational pull of dark matter and the baryonic matter, which includes ordinary matter like stars and gas. In the early universe, tiny density fluctuations developed due to quantum effects. As the universe expanded and cooled, gravity caused these fluctuation regions to evolve. The areas of higher density attracted more matter over time, forming filaments that became rich in galaxies. As galaxies merge and interact, they tend to align along these filaments, leading to a concentration of cosmic structures. These filaments often host galaxies, galaxy clusters, and streams of gas, contributing to ongoing star formation. Remarkably, the material in these filaments can also be traced by observing the diffusion of hydrogen gas and other elements, providing clues about the composition of the universe. The cosmic web structure reveals not just how galaxies are distributed, but also the intricate interplay of gravitational forces at work across vast distances. Each filament serves as a corridor through which matter flows, and studying these structures helps astronomers gain insights into the universe's evolution, the nature of dark matter, and the overall dynamics that govern cosmic behavior. The Great Attractor is a gravitational anomaly located in the direction of the constellation Centaurus that exhibits a powerful influence on the motion of galaxies in our local supercluster, known as the Laniakea supercluster. This mysterious region is responsible for drawing galaxies, including our Milky Way, towards itself at significant velocities. Understanding the Great Attractor involves unraveling both the nature of the structure itself and the cosmic forces at play. The Great Attractor is thought to be a massive concentration of galaxies and dark matter, making it a considerable gravitational focal point. Estimates suggest that it may contain several thousand galaxies, along with substantial amounts of unseen dark matter. This dark matter does not emit light or other forms of radiation, making it challenging to observe directly, but its presence can be inferred through its gravitational effects on visible matter. One of the significant challenges in studying the Great Attractor is its location behind the Milky Way's galactic plane. Dense clouds of gas and dust obscure our view, which complicates direct observations. Nevertheless, studies have indicated that the mass of the Great Attractor could be equal to approximately 10 million billion times the mass of the Sun, a staggering amount that provides the necessary gravitational pull. Beyond the Great Attractor itself lies the concept of larger cosmic structures, such as the Shapley concentration, which may be contributing factors to the motion of galaxies in our vicinity. These large-scale structures create a web-like framework of gravitational influences that direct the flow of galaxy clusters across vast distances. The Great Attractor serves as a point of interest in our attempts to understand the dynamic and interconnected nature of the universe's structure and the role of dark matter in shaping that architecture. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. Comprising about 25% of the universe, dark matter plays a crucial role in the overall structure and evolution of cosmic phenomena. Its existence was first inferred from observations of galaxies and galaxy clusters, where the visible mass alone could not account for the gravitational forces observed. The influence of dark matter becomes apparent when studying the rotation curves of galaxies. These curves measure how fast stars orbit around the galactic center. According to Newtonian physics, one would expect the stars farther from the center to rotate more slowly. However, observations indicate that stars maintain high velocities even at significant distances. This discrepancy suggests there is additional unseen mass exerting gravitational pull, stabilizing the galaxy and preventing it from flying apart. Dark matter also plays a vital role in the formation of the large-scale structure of the universe. During the early stages of the universe's evolution, dark matter contributed to the gravitational scaffolding around which visible matter clumped together. This clumping gave rise to the galaxies, clusters of galaxies, and vast cosmic filaments we observe today. The presence of dark matter is fundamental to creating the cosmic web architecture we see across the universe. Despite its prominence, dark matter remains elusive, with various candidates proposed to explain its nature, such as weakly interacting massive particles and axions. Research continues to uncover more about dark matter's properties and behaviors, particularly through experiments designed to detect its effects directly or indirectly. Understanding dark matter is paramount for astronomers, as it shapes the universe's history and ongoing evolution, influencing everything from galaxy formation to the cosmic microwave background radiation. The idea that dark matter could be composed of undiscovered particles is a leading hypothesis in contemporary astrophysics. Scientists propose several candidates for these particles, which could account for dark matter's gravitational effects while remaining undetectable by conventional means. The search for these elusive particles is an exciting area of research, as finding them would provide profound insights into the fundamental nature of the universe. One prominent candidate is weakly interacting massive particles, commonly referred to as WIMPs. WIMPs are theoretical particles predicted by certain extensions of the standard model of particle physics. They would interact via the weak nuclear force, which is significantly weaker than electromagnetic and strong forces, making them extremely difficult to observe directly. Experiments are ongoing to detect WIMPs through various sophisticated methods, but as of now, none have succeeded. Another intriguing possibility is the existence of axions, hypothetical particles that could emerge from theories attempting to unify the forces of nature. Axions are predicted to be lightweight and would also have minimal interactions with ordinary matter. If they exist, they could form a cosmic background that permeates the universe, contributing to the gravitational effects attributed to dark matter. Additionally, more exotic candidates such as sterile neutrinos and primordial black holes have been proposed. Each of these candidates presents unique properties and behaviors that could potentially fit the observed phenomena associated with dark matter. The endeavor to identify and study these particles encompasses vast projects, including underground laboratories, particle accelerators, and even astronomical observations. The discovery of any of these particles would not only confirm their role in dark matter, but also lead to groundbreaking advancements in our understanding of physics and the universe's composition. Dark energy is a mysterious force that is believed to be responsible for the accelerated expansion of the universe. This phenomenon was first observed in the late 1990s, when astronomers studying distant supernovae discovered that these cosmic explosions were farther away than expected. Rather than losing speed as the universe expands, it appeared that the expansion was actually speeding up, indicating the influence of a repulsive force. The leading explanation for dark energy is that it constitutes about 70% of the total energy density of the universe, dominating its overall dynamics. Unlike matter, which attracts via gravitational pull, dark energy exerts a negative pressure that pushes structures apart. This negative pressure tends to increase as the universe expands, leading to a greater acceleration of expansion over time. One of the most well-known models describing dark energy is the cosmological constant proposed by Albert Einstein. This constant suggests that dark energy is a characteristic of space itself, meaning that as more space is created in an expanding universe, the total effect of dark energy increases. This model aligns well with observations, yet it leaves open questions about the nature of dark energy and why it has the properties it does. Alternative theories also exist, including dynamic forms of dark energy that could evolve over time. These theories suggest that the effect of dark energy might vary, potentially changing the universe's fate in the far distant future. Understanding dark energy remains one of the most significant challenges in modern cosmology, as its peculiar properties challenge our fundamental understanding of gravity and the underlying fabric of the universe. Through ongoing observations and experiments, scientists continue to unravel the mysteries surrounding this enigmatic force driving the cosmos apart. The concepts of dark matter and dark energy both address the enigmatic components of the universe that profoundly influence its structure and behavior. However, they represent different phenomena and serve distinct roles in the cosmos. Exploring the relationship between them can deepen our understanding of the universe, even as they remain fundamentally separate in nature. Dark matter is primarily tied to the gravitational framework of the universe. It comprises a significant portion of the universe's mass, influencing the motion of galaxies and the formation of large-scale structures. Its presence is crucial for explaining the observed behaviors of galaxies and galaxy clusters, as the visible matter alone does not provide enough gravitational influence. Dark matter acts as a stabilizing force, helping to bind galaxies together and shape the cosmic web. On the other hand, dark energy is associated with the accelerated expansion of the universe. It constitutes a vast majority of the universe's total energy density and exerts a repulsive force that drives galaxies apart. While dark matter behaves like a form of mass, exerting gravitational attraction, dark energy works against gravity, leading to a more rapid expansion of space itself. Despite their differing roles, some theories suggest there may be a deeper connection between dark matter and dark energy. For instance, they could emerge from a common origin, reflecting aspects of a more comprehensive framework that we have yet to discover. Some scientific models propose that interactions between dark matter and dark energy might influence cosmic evolution in subtle ways, although definitive evidence remains elusive. Overall, while dark matter and dark energy coexist in the universe and both impact its evolution, they serve distinct purposes. Ongoing research aims to demystify these two fundamental components and explore any potential connections, contributing to a more cohesive understanding of the intricate workings of the cosmos. Alternative theories of gravity pose intriguing possibilities for explaining the effects commonly attributed to dark matter and dark energy. These theories arise from the desire to address some of the inconsistencies and challenges faced in standard cosmological models, particularly those involving the gravitational behavior of matter on cosmic scales. One notable alternative theory is modified Newtonian dynamics, often referred to as MOND. This theory proposes that at very low accelerations, such as those found in the outskirts of galaxies, the laws of gravity differ from Newton's law. By modifying the gravitational dynamics, MOND aims to account for the observed rotational curves of galaxies without invoking dark matter. While MOND successfully explains certain galactic phenomena, it struggles to comprehensively address large-scale structures and the cosmic microwave background. Another alternative is the theory of scalar tensor gravity, which includes additional scalar fields that interact with gravity. These scalar fields can modify gravitational behavior in a way that can mimic the effects of dark energy by introducing a dynamic component to space-time. In some models, changes in the scalar field can lead to an accelerated expansion of the universe without the need for dark energy. However, these theories still face scrutiny and must be reconciled with numerous observational data. Furthermore, some researchers are exploring theories that unify gravity with quantum mechanics, such as loop quantum gravity or string theory. These ideas could potentially offer new insights into the nature of both gravity and the unseen components of the universe, linking dark matter and dark energy to fundamental aspects of reality. While alternative theories of gravity present fascinating avenues for understanding cosmic phenomena, it is essential to note that the existing framework involving dark matter and dark energy is robust and well supported by a wide range of observational data. The quest to find answers remains active, with ongoing research focused on testing these alternative theories against empirical evidence from cosmic observations. Exploring these ideas not only deepens our understanding of gravity, but also enhances our grasp of the distinct yet interconnected components that shape the universe. Fast radio bursts, or FRBs, are intense and brief flashes of radio waves originating from distant galaxies. Discovered accidentally in 2007, these enigmatic phenomena have captured the attention of astronomers due to their potency, duration, and elusive nature. Each burst lasts only a few milliseconds, yet can release energy equivalent to what the sun emits in an entire day, prompting researchers to investigate their origins and implications for the universe. The exact cause of FRBs is still largely unknown, leading to several intriguing theories. One prominent hypothesis suggests that they may be generated by neutron stars, particularly magnetars, which are highly magnetic and dense remnants of supernova explosions. When a magnetar undergoes a starquake, The violent release of energy could potentially result in a burst of radio waves that we detect as an FRB. This model seems particularly plausible as some FRBs have been observed repeating, hinting at a source that produces bursts under certain conditions. Another possibility is that FRBs could originate from cataclysmic events involving black holes or the merger of compact objects, such as neutron-star collisions. The energy produced during such dramatic cosmic incidents could produce radio waves detectable across vast distances. This connection to high-energy astrophysical events offers insights into cosmic processes and the behavior of matter under extreme conditions. While researchers have made significant strides in locating some sources of FRBs, the full scope of their origins remains a mystery. Ongoing observations and studies aim to determine whether these bursts arise from common astrophysical processes or represent a wider variety of phenomena. Detecting FRBs has opened a new window into the study of the universe, offering potential insights into the evolution of galaxies and the nature of extreme astrophysical conditions. As technology advances and observational capabilities expand, the quest to understand the origin of FRBs continues, promising exciting discoveries ahead. The idea that some fast radio bursts, or FRBs, might be signals from advanced alien civilizations is a fascinating but highly speculative hypothesis that has captured the imagination of both scientists and the public. While the origins of FRBs remain largely mysterious, the thought that extraterrestrial intelligence could be behind some of these bursts adds an intriguing layer to the search for life beyond Earth. Proponents of this idea often point to the regularity and certain characteristics of some repeating FRBs that could suggest a technological source. Unlike natural cosmic phenomena, which often have unpredictable and varied patterns, artificial signals might have a more structured and consistent nature. Researchers have even initiated efforts to analyze FRBs for patterns or behaviors that might indicate intentional communication rather than random astrophysical events. However, there are significant challenges to validating the extraterrestrial hypothesis. The sheer variety of FRBs and their detection from different galaxies suggest that they likely originate from natural astrophysical processes rather than artificial signals. As scientists have studied and refined our understanding of radio bursts, many have concluded that the characteristics of these bursts align more closely with high-energy cosmic events, such as neutron star activities or black hole interactions. The search for extraterrestrial intelligence encompasses broader efforts, including dedicated programs like the Search for Extraterrestrial Intelligence, commonly known as SETI. These programs actively scan the skies for signals that exhibit signs of intelligence, distinguishing them from naturally occurring radio waves. Although the notion of FRBs being linked to extraterrestrial civilizations is a tantalizing possibility, current scientific consensus leans towards interpreting these phenomena as products of cosmic forces rather than alien communications. As research progresses, the mystery of FRBs may ultimately reveal more about the universe's nature, possibly informing our understanding of life's existence elsewhere. Gamma-ray bursts, or GRBs, are extraordinarily energetic explosions that release intense bursts of gamma radiation, the most powerful form of electromagnetic radiation. These events can outshine entire galaxies for brief periods, typically lasting from a few milliseconds to several minutes. Understanding the causes of gamma-ray bursts has become a major focus in astrophysics, with several leading theories explaining their origins. Most gamma-ray bursts are classified into two categories: long-duration and short-duration bursts. Long-duration GRBs, lasting over 2 seconds, are generally associated with the collapse of massive stars during supernova events. When a massive star exhausts its nuclear fuel, its core collapses under gravity, leading to the formation of a black hole. This process can result in the formation of highly focused jets of material that travel at nearly the speed of light, producing intense gamma radiation as they burst out of the star's outer layers. The subsequent explosion illuminates the cosmos, becoming one of the most energetic events in the universe. In contrast, short-duration GRBs, lasting less than 2 seconds, are typically linked to the merger of compact objects, such as neutron stars or black holes. As these dense celestial bodies spiral inward and eventually collide, they release tremendous amounts of energy in the form of gamma rays, along with gravitational waves. Observations of these bursts have led to significant advances in the field of gravitational wave astronomy, providing crucial insights into the behavior of neutron stars and the conditions under which black holes form. The study of gamma-ray bursts is critical not only because of their intrinsic energy but also for the information they carry about the early universe. By analyzing the light from gamma-ray bursts and their afterglows, astronomers can probe the conditions of the universe at great distances. This research continues to contribute to our understanding of stellar evolution, the formation of exotic cosmic objects, and the behavior of matter under extreme circumstances, all while revealing fundamental aspects of our universe's history. The phenomenon of stars seemingly disappearing without a trace is primarily linked to two processes: the end stages of stellar evolution and the particular circumstances surrounding their collapse. Stars generally follow a life cycle that culminates in dramatic events, but in some cases the outcome can be elusive or misleading. One of the most intriguing explanations for disappearing stars involves supernovae, which are explosive deaths of massive stars. Traditionally, when such a star exhausts its nuclear fuel, it may undergo a supernova explosion, resulting in a bright flash of light visible across vast distances. However, in certain cases, the core of the star collapses into a black hole, and the outer layers are ejected with minimal luminosity. If the supernova is not energetic enough to produce a noticeable burst, the star can appear to vanish without leaving behind observable remnants, such as a bright explosion. In other instances, stars can also be obscured by interstellar material. Cosmic dust and gas can obscure our view of celestial objects, causing stars to seemingly fade from sight. In regions of dense star formation or within complex nebulae, light from certain stars might be absorbed or scattered, rendering them invisible to our telescopes. Until improved observational techniques or instruments reveal these stars, they may be thought to have disappeared. Moreover, some variables or transient phenomena can contribute to the impression that stars vanish. For example, certain types of variable stars experience fluctuations in brightness, and when they enter a dim phase, they may seem to have disappeared. New observational techniques, particularly in different wavelengths such as infrared or radio, have enhanced our ability to detect such stars, potentially uncovering those once thought lost. The study of these disappearing stars not only deepens our understanding of stellar life cycles, but also emphasizes the importance of detecting and interpreting a wider range of astronomical signals. Ongoing research continues to explore the mysterious mechanisms behind these events, revealing the dynamic and sometimes hidden nature of the cosmos. The WOW signal is one of the most intriguing and mysterious events in the search for extraterrestrial intelligence. Detected on August 15th in 1977 by astronomer Jerry R. Ehman using the Big Ear radio telescope, it was an intense burst of radio waves that lasted for 72 seconds. The signal appeared to come from the direction of the Sagittarius constellation, specifically from a point near the star Chi Sagittarii. What made this signal remarkable was its strong intensity and the fact that it was at a frequency of 21 centimeters, which is significant because it is known to be a wavelength where hydrogen, the most abundant element in the universe, radiates. This could indicate that the signal might have originated from an intelligent source rather than from typical cosmic phenomena like stars or planets. Ehman was so astonished by the data that he circled the alphanumeric string that represented the signal and wrote "WOW" in the margins, giving it its iconic name. Despite numerous follow-up observations and attempts to detect the signal again, it has never been detected again since that initial reading. This raises fascinating questions about the signal's origin and nature. Some scientists have proposed that it could have been a comet emitting a radio wave, while others suggest it might have been the result of terrestrial interference or possibly even an intentional transmission from an alien civilization. However, none of these explanations have been definitively proven. The lack of subsequent detections only adds to the allure of the WOW signal. It remains an important part of the ongoing conversation about the search for extraterrestrial life and our understanding of the universe. As our technology advances and our searches expand, scientists continue to seek out signals that might provide us with clues about life beyond our planet. with the wow signal standing as a tantalizing reminder of the mysteries that still remain in the cosmos. The potential for Earth-like exoplanets to harbor life is one of the most exciting areas of astrobiological research. As of now, astronomers have discovered thousands of exoplanets, some of which are located within the habitable zone of their stars. This is the region where conditions may be just right for liquid water to exist, a critical ingredient for life as we know it. One of the most promising candidates is Proxima Centauri b, which orbits our closest neighboring star, Proxima Centauri. This exoplanet resides within its star's habitable zone, suggesting that it could possess conditions suitable for liquid water. However, there are still many unknowns, such as the atmosphere's composition and the presence of a magnetic field that could protect biological processes from harmful cosmic radiation. Another noteworthy example is Kepler 186f, which is roughly 1.1 times the size of Earth and also orbits within its star's habitable zone. Its composition and atmosphere remain largely unknown, but the very nature of its discovery has excited scientists. The search for biosignatures or signs of life in its atmosphere will be a key focus of future studies. And while these planets may have the right conditions for life, it's important to remember that the mere presence of Earth-like characteristics does not guarantee that they harbor life. Conditions on those planets could differ significantly from what we experience on Earth. Thus, the quest to find life beyond our planet is still ongoing, with each new discovery bringing us closer to answering this profound question about our place in the universe. The exploration continues, driven by our innate curiosity and desire to understand if we are truly alone in the cosmos. The search for microbial life within our solar system is a fascinating endeavor, particularly in areas like Mars and Europa, where conditions might support life, even if only in microbial forms. Mars has been a prime focus of exploration due to evidence that it once had liquid water on its surface. Various missions, including the rovers Opportunity and Curiosity, have discovered minerals that form in the presence of water, suggesting a wetter and potentially more hospitable past. Recent missions, such as those conducted by the Perseverance rover, have aimed to search for biosignatures, indicators that life either existed or currently exists on Mars. Additionally, the discovery of seasonal methane fluctuations in the Martian atmosphere raises intriguing possibilities, as methane can be a byproduct of biological activity. While the existence of life has not been confirmed, the data from current and future missions could enhance our understanding of the planet's potential to support microbial life. Europa, one of Jupiter's moons, presents another exciting opportunity in the search for life. Beneath its icy crust lies a vast ocean of liquid water, which could harbor the conditions necessary for microbial life. This subsurface ocean is kept warm by gravitational interactions with Jupiter, creating a unique environment that may have chemical compounds required for life. Missions like NASA's upcoming Europa Clipper aim to study the moon's surface and investigate its potential habitability more closely. As we refine our technology and increase our understanding of extreme environments on Earth, we become more optimistic about the chances of finding microbial life in our own solar system. While the evidence so far is circumstantial, the ongoing exploration promises to reveal more about these intriguing worlds and whether they might be home to life, albeit in the tiniest forms. Each discovery brings us closer to answering the age-old question of whether we are alone in the cosmos. The discovery of alien life, even if it were just microbial, would fundamentally transform our understanding of the universe and our place within it. Such a revelation would affirm that life is not an exclusive characteristic of Earth, but rather a more common phenomenon across the cosmos. This realization would challenge the long-held notion that Earth is unique, prompting profound philosophical and scientific discussions about life's resilience and adaptability. The implications extend beyond science into culture and society. Religions and belief systems might reevaluate their teachings, attempting to reconcile the existence of life beyond Earth with spiritual narratives. Conversely, the confirmation of extraterrestrial life would likely spark an unprecedented wave of interest in science and exploration, compelling humanity to invest more in space research and planetary exploration. The notion of other life forms would inspire questions about communication, the nature of intelligence, and the potential for interstellar collaboration or conflict. Moreover, locating microbial life on another planet would fuel inquiries about the evolution of life and the necessary conditions for it to thrive. Scientists would seek to understand if these organisms share any biochemical similarities with Earth life or if they utilize entirely different processes. This could expand our definition of life itself, prompting new theories in biology and astrobiology regarding life's forms and habitats. Ultimately, whether single-celled or complex, the discovery of alien life would ignite our imaginations, urging humanity to ponder the broader universe. It would serve as a reminder of our shared cosmos, igniting a quest not only to learn about these life forms, but also to consider our responsibilities as stewards of our own planet. The prospect of alien existence would spur us to envision a future where we can look beyond our planet and explore the endless possibilities that the universe still holds. The quest to detect signs of alien civilizations involves innovative and diverse methods that encompass a range of scientific disciplines. One of the foremost techniques is the search for radio signals, known as the Search for Extraterrestrial Intelligence Project. This method involves monitoring specific frequencies of radio waves for patterns or signals that would suggest intentional communication. As the universe is filled with background noise, any distinct, non-random signal would stand out as a potential indicator of an intelligent presence. Another promising approach is the examination of exoplanet atmospheres for biosignatures or technosignatures. Scientists can analyze the light passing through a planet's atmosphere when it transits in front of its star. By studying the resulting spectrum, they can detect the presence of gases such as oxygen, methane, and other chemicals that might suggest biological processes. Any combination of gases that are not in equilibrium could point towards industrial activity, acting almost like a signature of advanced civilizations. Transit observations like those used in the Kepler mission can also reveal unusual patterns that might indicate large structures built by alien civilizations. These could include megastructures like Dyson spheres, hypothetical constructs built around stars to capture energy. Any significant alteration in a star's brightness could prompt further investigation to determine if it is an artificial structure or merely a natural phenomenon. Additionally, advancements in optical SETI have emerged as another method. This involves scanning for laser pulses or other forms of optical emissions that might suggest advanced technology. Researchers believe that at certain distances, a focused laser beam may be more efficient than radio waves for communication. As technology progresses, these diverse methods ensure that the search for alien civilizations remains dynamic and adaptive, keeping the hope alive that one day we will uncover evidence of life beyond our planet. The absence of conclusive evidence for alien life, despite the vastness of the universe, can be attributed to several factors that influence our search. One prominent reason is the sheer scale of the cosmos. With an estimated 2 trillion galaxies, the distances between stars and planets are immense, making it challenging to conduct thorough searches. Even with our most advanced telescopes and space missions, we are limited in the volume of space we can effectively explore at any given time. Moreover, the possibility of alien civilizations existing in vastly different technological stages plays a significant role. It is plausible that we are either too advanced or too primitive to detect each other. Civilizations could exist simultaneously in different stages of technological development, with some having advanced to the point of being able to communicate across the stars, while others may still be in their early evolutionary phases. There is also the chance that some civilizations might have existed long ago and perished, leaving no evidence behind. Another factor is the nature of communication itself. If advanced civilizations communicate using methods we have yet to discover or understand, such as different frequencies, technologies, or even forms of intelligence beyond our scope, we might not recognize the signals they send. Furthermore, the environmental conditions necessary for life, particularly intelligent life, may be quite rare in the universe. This raises the question of whether we are indeed looking in the right places and using the right methods. Lastly, the Fermi paradox encapsulates this dilemma by asking, if extraterrestrial civilizations are common, where is everyone? This paradox highlights the contradiction between high estimates of the potential for alien life and the lack of evidence for their existence. As our exploration continues and our technologies evolve, we remain hopeful, understanding that each new discovery brings us closer to answering this profound question, and perhaps one day we will uncover the evidence we seek. When matter and information falls into a black hole, it encounters the event horizon, which is the boundary beyond which nothing can escape, not even light. As matter approaches this threshold, it is subjected to extreme gravitational forces that stretch and compress it, a phenomenon known as spaghettification. This process occurs because the gravitational pull is significantly stronger at the point of closest approach, leading to the object being elongated and ultimately torn apart as it moves deeper into the black hole. The fate of information in particular raises profound questions in physics. According to classical interpretations, when matter crosses the event horizon, the information contained within it is lost to the outside universe. This notion poses a dilemma known as the information paradox. Quantum mechanics suggests that information cannot be destroyed, leading theorists to grapple with the implications of this contradiction. If information about the matter that fell into a black hole does not disappear, it must be stored or preserved in some form. Recent theories have proposed mechanisms for how information might be retained, such as the idea that it could be encoded on the event horizon itself, a concept known as holography. This suggests that all the information about what has fallen into a black hole is somehow imprinted on its surface area rather than lost within. Other theories explore notions like black hole firewalls, which posit that an energetic boundary exists at the event horizon, forcing radical rethinking of our understanding of physics. These questions surrounding the nature of matter, information, and black holes have significant implications for our overall understanding of the universe. As our knowledge of black holes expands through observations and theoretical advancements, we may eventually find answers that could reconcile these core challenges in physics, potentially reshaping our understanding of reality itself. The intriguing concept of black holes as gateways to other universes or dimensions has captivated both scientists and enthusiasts alike. While traditional physics views black holes as regions of extreme gravitational pull from which nothing can escape, theories in theoretical physics, particularly those involving advanced concepts like quantum mechanics and string theory, introduce the possibility of black holes leading to other realms or dimensions. One fascinating idea is that of a wormhole, a hypothetical tunnel-like structure that connects two separate points in space-time. If such wormholes exist and are stable enough, they might act as shortcuts, allowing travel between different locations in our universe, or even different universes entirely. Some theories suggest that the core of a black hole could contain a wormhole that leads to another dimension, providing an entirely different universe governed by its own set of physical laws. However, these ideas remain speculative and face significant scientific hurdles. The conditions at the singularity, the point at which gravity is thought to become infinite in a black hole, create challenges for our current understanding of physics. Moreover, any potential wormhole would likely be extremely unstable and collapse almost instantaneously, making practical traversal nearly impossible. This aligns with the notion of the no-hair theorem, which suggests that black holes are characterized only by mass, charge, and angular momentum, obscuring any detailed information that might reveal additional pathways. Despite the current limitations, exploring black holes as potential gateways remains an enticing aspect of theoretical astrophysics. As we deepen our understanding of quantum gravity and the fundamental nature of the universe, the possibility of black holes connecting to other dimensions could provide valuable insights into the fabric of reality. Thus, while we have not yet found empirical evidence to support the notion of black holes serving as portals, the exploration of this idea continues to inspire scientific inquiry and imagination. Supermassive black holes, those with masses millions to billions of times that of our Sun, are found at the centers of most galaxies, including our Milky Way. The exact processes behind their formation are still subjects of intense research and debate, but several theories provide insights into how these colossal entities come into existence. One leading theory suggests that supermassive black holes form from the merger of smaller black holes and massive stars. In the early universe, conditions were such that many dense star clusters existed, some producing massive stars that eventually went supernova. The remnants of these massive stars could collapse into black holes. As these smaller black holes formed and were drawn towards the center of their host galaxies due to gravity, they could merge together, forming larger black holes over time. Another perspective posits that supermassive black holes might originate from the direct collapse of massive gas clouds in the early universe. In regions of particularly high density, gas could rapidly collapse under its own gravitational pull, bypassing the typical star formation process. This collapse could lead to a massive black hole forming very quickly, potentially during the first few 100 million years after the Big Bang. This scenario is supported by observations of extremely massive black holes in young, distant galaxies. Additionally, interactions and mergers between galaxies play a crucial role in the evolution of supermassive black holes. As galaxies collide, their central black holes can also merge, leading to the formation of even larger supermassive black holes. This gravitational dance can fuel active galactic nuclei, regions around black holes that emit tremendous amounts of energy as gas and matter are consumed. These processes highlight the dynamic interplay between gravity and matter in the universe, bringing us closer to understanding how the massive structures we observe today came to be. As telescopes and detection methods improve, scientists hope to unravel the mysteries surrounding the formation and growth of supermassive black holes, raising further questions about their influence on galaxy formation and evolution. The relationship between black holes and the formation and evolution of galaxies is a complex and dynamic interplay that has profound implications for our understanding of the cosmos. Supermassive black holes, typically residing at the centers of galaxies, are believed to influence their formation and evolution in several significant ways. One of the key aspects of this relationship is the role supermassive black holes play in regulating star formation within their host galaxies. As they accrete matter and radiate energy, they can produce powerful jets and winds that influence the surrounding gas. These outflows can suppress or trigger star formation by blowing gas away from the central regions or causing gas to cool and collapse into new stars. This feedback mechanism helps to shape the galaxy's structure and growth over cosmic time. Moreover, the presence of a supermassive black hole is often correlated with the characteristics of its host galaxy. Observations show that more massive black holes are typically found in more massive galaxies, suggesting a co-evolutionary process. This relationship is exemplified by the correlation between the mass of the black hole and the velocity dispersion of stars in the galaxy's bulge. This correlation indicates that the formation of the black hole and the galaxy may be linked during the early stages of their evolution. The merger of galaxies further underscores the connection between black holes and galactic evolution. When two galaxies collide, their central black holes are also engaged in the drama of merging. The resulting gravitational interactions can lead to the formation of larger supermassive black holes and can profoundly influence the new galaxy's structure and dynamics. These events are often accompanied by bursts of star formation and changes in the galaxy's morphology, showcasing the interconnectedness of these celestial phenomena. As research continues to unravel these relationships, scientists gain crucial insights into the formation, growth, and evolution of galaxies in the cosmic tapestry. The interaction between black holes and galaxies underscores the importance of understanding the universe's most massive objects in shaping the structures we observe today, revealing the intricate dance between gravity, matter, and evolution across cosmic time. Within the classical framework of physics, once something crosses the event horizon of a black hole, it cannot escape. The gravitational pull is so strong that not even light has the capability to break free. However, there are certain phenomena related to black holes that allow for the consideration of escape in different contexts, primarily involving the effects of quantum mechanics. One intriguing concept is Hawking radiation, proposed by physicist Stephen Hawking in 1974. According to quantum theory, empty space is not truly empty, but instead is filled with virtual particles that constantly form and annihilate. Near the event horizon, it is possible for one of these virtual particle pairs to be separated, with one particle falling into the black hole while the other escapes into space. This escaping particle would be detected as radiation, allowing information to be emitted from the black hole over time. While Hawking radiation is incredibly weak and has yet to be observed directly, it presents a theoretical means through which energy and particles can escape from black holes, effectively suggesting that black holes could eventually evaporate, losing mass in the process. Another scenario involves the environment surrounding a black hole. Material outside the event horizon can be drawn in by the black hole's gravitational influence and form an accretion disk. As matter spirals in, it heats up, producing powerful jets of particles and radiation that shoot out along the poles of the black hole. These jets can carry energy and information away from the black hole, demonstrating that while nothing can escape once inside, the energetic interactions around it can still produce observable effects beyond the event horizon. The notion of escape from a black hole is fundamentally linked to our understanding of gravity, quantum mechanics, and the boundaries of current theories. As research continues into the complexities of black holes, especially regarding Hawking radiation and the nature of spacetime, scientists remain engaged in exploring whether our understanding will shift to reveal more about how these enigmatic objects interact with the universe around them. Time travel has long captivated human imagination, not only through science fiction, but also within the realm of theoretical physics. While no empirical evidence supports the feasibility of time travel, certain theories in physics suggest that it could be, at least theoretically, achievable under specific conditions. One of the most studied concepts is based on Albert Einstein's theory of relativity. According to this theory, time is not a constant. Rather, it can be affected by factors such as speed and gravity. This phenomenon is known as time dilation. For instance, as an object moves closer to the speed of light, time slows down for it relative to an outside observer. This means that if a spacecraft could travel at relativistic speeds, astronauts aboard could theoretically jump forward in time relative to people remaining on Earth. However, this form of time travel is essentially a progression into the future rather than the ability to revisit the past. Another intriguing theoretical proposal comes from the concept of wormholes, sometimes referred to as shortcuts through spacetime. These hypothetical tunnels could connect distant points in the universe or different times, creating potential paths for time travel. However, the existence of stable wormholes is still an open question in physics. Even if they do exist, creating or maintaining a wormhole would likely require exotic matter with negative energy density, which has not been discovered. The idea of closed time-like curves, which are paths in spacetime that loop back on themselves, offers another avenue for theoretical exploration. Such curves could allow for time travel to the past, but they also introduce paradoxes, such as the grandfather paradox, where a time traveler could potentially prevent their own existence. These paradoxes raise fundamental questions about causality, challenging our understanding of time and reality. While these theories present fascinating possibilities, practical time travel remains speculative and largely theoretical. Current technological limitations and our understanding of the laws of physics do not offer concrete methods for achieving it. Nonetheless, the continued exploration of ideas surrounding time, wormholes, and the fabric of space-time ensures that the concept of time travel remains an intriguing topic of scientific inquiry and philosophical debate. Time travel poses a multitude of fascinating implications and paradoxes that challenge our understanding of physics, causality, and reality itself. One significant implication revolves around the concept of causality, the principle that cause precedes effect. Time travel, particularly to the past, raises the question of whether it is possible to change events that have already occurred, leading to potential contradictions in the timeline. One of the most famous paradoxes associated with time travel is the grandfather paradox. This scenario describes a time traveler who goes back in time and inadvertently prevents their grandfather from meeting their grandmother. If that were to happen, the time traveler would never have been born, which raises the question, how could they have traveled back in time in the first place? Such paradoxes highlight the complications that arise when considering changes to established events and the potential for contradictory outcomes. Another thought-provoking aspect of time travel involves alternate timelines or parallel universes. Some theories suggest that if someone were to change an event in the past, it could create a divergent timeline rather than altering the original one. In this perspective, the time traveler would enter a new universe where the changes they made would not affect the original reality from which they came. This idea introduces complexities surrounding personal identity and causality, raising questions about the implications for different versions of oneself existing simultaneously across timelines. While theories like the many worlds interpretation of quantum mechanics offer potential resolutions to such paradoxes, they also bring their own set of implications. For instance, if time travel could lead to the creation of new realities, one might ponder the ethical consequences of influencing past events and the responsibility associated with altering timelines or destinies. Ultimately, the implications and paradoxes of time travel invite deep philosophical and scientific discussions. While current physics does not offer any practical means to achieve time travel, the examination of these paradoxes encourages exploration into the fundamental nature of time, space, and reality itself. As our understanding of the universe advances, so too will our engagement with the complex and thought-provoking consequences of time travel theories. The idea of time travelers from the future visiting our time is an intriguing concept that raises questions about evidence and the nature of time itself. While there is no direct empirical evidence to support the notion of time travelers among us, various cultural narratives, anecdotal reports, and theoretical possibilities have sparked fascination and speculation. One argument against the likelihood of time travelers being present today stems from the absence of irrefutable proof. If time travel were possible and individuals from the future chose to visit the past, one would expect to encounter clear indicators or substantial evidence of their presence, remarkable technologies, unexplained phenomena, or even documented encounters. Despite numerous claims of sightings and mysterious individuals, none have been substantiated to provide definitive proof of time travel. Furthermore, theories in physics such as causality and potential paradoxes complicate the idea of time travelers influencing past events. If time travel were allowed, it raises questions about why we haven't observed any historical changes or interactions that can be definitively attributed to time travelers. Such a scenario suggests that if time travel does exist, future beings might have strict regulations against intervening in the past, akin to the prime directive in science fiction narratives, which would prevent them from altering history to avoid catastrophic paradoxes. Conversely, the nature of evidence for time travelers would likely differ from typical expectations. The advanced technology and understanding of the future might manifest in subtle ways, making detection difficult. Some theories suggest that time travelers could blend inconspicuously into society, adopting present-day identifiers to avoid drawing attention to themselves. However, this speculation remains largely in the realm of fiction rather than scientific discussion. While the idea of time travelers visiting us captures our imagination and raises captivating questions about the nature of time and existence, the absence of concrete evidence keeps it firmly in the realm of theoretical speculation. As our understanding of physics and the universe develops, so too does the exploration of ideas surrounding time travel, yet for now the evidence remains elusive. Time behaves very differently in extreme conditions, particularly near a black hole, due to the intense gravitational fields involved. According to Einstein's theory of general relativity, gravity is not merely a force but a curvature of space-time caused by massive objects. As a result, when one approaches a black hole, time experiences significant dilation effects, meaning it passes at different rates depending on the proximity to the black hole. Inside the strong gravitational field of a black hole, particularly near the event horizon, time slows down significantly compared to regions far away. For an observer falling towards the black hole, time would appear to tick normally for them, but an external observer watching from a safe distance would see the falling individual moving increasingly slower as they approach the event horizon. This effect highlights the relative nature of time. What feels like a short journey could appear drawn out and prolonged to external observers, demonstrating profound differences in temporal experience based on gravitational influence. In extreme cases, once an object crosses the event horizon, classical understanding suggests it can no longer escape or return. For the observer who has crossed the threshold, they would theoretically experience time normally until reaching the singularity, where current physics breaks down and predictions become unreliable. The implications of such extreme conditions indicate that the very fabric of time and space is significantly altered in the vicinity of a black hole. Furthermore, these effects extend beyond black holes, as any massive object can influence the flow of time. For example, satellites in orbit experience slight time dilation compared to clocks on Earth's surface due to their speed and distance from Earth's gravitational field. This phenomenon is known as gravitational time dilation, and it has practical implications, such as the necessity of adjusting the global positioning system satellites to maintain accuracy. Overall, the behavior of time in extreme gravitational conditions challenges our intuitive understanding of it as a constant. The study of these effects not only enriches our grasp of fundamental physics, but also invites deeper exploration into the nature of the universe itself. Documented cases of time anomalies or time slips are often met with skepticism but have intrigued both researchers and enthusiasts alike. These occurrences typically involve individuals reporting experiences where they perceive time differently than what is recorded by clocks or calendars. In some accounts, people have experienced sudden shifts, finding themselves in a different time period, albeit briefly. For instance, there are stories of travelers who claim to have encountered historical settings or figures that seem to pull them away from their current reality. Despite the tantalizing nature of these stories, scientific scrutiny remains. Researchers argue that psychological phenomena or altered states of consciousness might explain many of these experiences rather than any actual bending of time itself. The brain's perception of time can be affected by various factors, such as stress or trauma, leading to what may feel like time abnormalities. Thus, while these narratives capture the imagination, they do not provide empirical evidence for time travel or genuine time anomalies. Though science has not validated the existence of time slips, they serve as a fascinating lens through which to explore human consciousness and our understanding of time. The insistence on documenting these experiences may reflect our deeper existential questions about reality, the passage of time, and whether we fully grasp how these concepts intersect with our lives. The concept of our universe existing among countless parallel universes is a captivating idea that stems from theories in quantum physics and cosmology. This notion, often referred to as the multiverse, suggests that what we perceive as our singular universe could actually be one of many, each with its own distinct laws of physics and variations of reality. Theoretical physicists propose various multiverse models that stem from different interpretations of quantum mechanics, cosmic inflation, and string theory. One intriguing model is the many worlds interpretation of quantum mechanics, which posits that every time a quantum event occurs, like a particle being in one state or another, the universe splits into different branches. Each branch represents an alternate outcome, creating a potentially infinite number of realities existing simultaneously. This idea challenges our conventional understanding of causality and choice, raising profound questions about fate and free will. Similarly, the cosmic inflation theory suggests that during the very early moments after the Big Bang, regions of space expanded rapidly, leading to bubble universes, each encapsulated in its own space-time. This creates an environment where universes could develop entirely different physical characteristics based on their initial conditions, further enriching the multiverse concept. While these theories are mathematically sound and intriguing, direct evidence for the existence of such multiverses remains elusive. The implications of a multiverse extend beyond just theoretical musings. They may impact how we understand fundamental principles of reality, such as time and existence. If our universe is merely one of many, it invites both excitement and humility in considering our place in the cosmic tapestry. It stirs curiosity about what forms of life and structures might exist beyond our observable limits, inviting us to ponder not just the universe we inhabit, but the infinite possibilities that may lie beyond it. Evidence for the existence of parallel universes remains largely theoretical, as direct observation has proven challenging. However, scientists have proposed several compelling ideas based on interpretations of existing data in physics and cosmology. One key area is quantum mechanics, particularly the many worlds interpretation, which suggests that every possible outcome of a quantum event occurs in its own separate universe. While this does not provide physical evidence, it offers a coherent framework within which parallel realities could exist. Cosmic inflation theory provides another point of interest. It posits that shortly after the Big Bang, the universe underwent rapid expansion, which could lead to the formation of bubble universes. Each of these bubbles might develop unique physical properties. While no bubbles have been directly observed, disparities in the cosmic microwave background radiation could hint at interactions between neighboring universes during this inflationary period. Some researchers are investigating these faint signatures, looking for patterns that might support a multiverse scenario. Mathematical models also play a significant role in the discussion of parallel universes. String theory, which aims to unify the fundamental forces of nature, predicts many possible configurations of dimensions that could imply multiple expansive realities. While these models provoke thought and inspire theoretical research, it is crucial to note that mathematics alone does not serve as conclusive evidence. Actual physical validation remains necessary for broader acceptance in the scientific community. Ultimately, while various theories suggest that parallel universes could exist, rigorous experimental evidence is still out of reach. Scientists continue to explore and debate these possibilities, pondering how our understanding of physics might evolve. The notion of parallel universes invites us to consider the broader implications of our universe and the potential existence of entirely different realms beyond our own. stimulating both scientific inquiry and public imagination. Parallel universes, if they exist, could vastly differ from our own in a multitude of ways, depending on the underlying principles guiding each universe. One possibility is that some universes may have different physical constants which determine the fundamental forces of nature. For example, a universe with a stronger gravitational force might give rise to completely different structures, potentially affecting the development of life itself. Alternatively, other universes might operate under entirely different laws of physics, perhaps allowing for phenomena that are unimaginable within our current framework. In addition to variations in physical laws, parallel universes could host alternate histories, leading to divergent timelines. Events that shape our reality, such as the outcomes of significant historical moments, could unfold differently in these alternative universes. This raises fascinating questions about identity and reality. In some realms, we might find versions of ourselves experiencing distinct lives. This possibility captivates the imagination and offers an enticing glimpse into what might be beyond our limited perception. Detecting or interacting with these parallel universes presents significant challenges. Current scientific tools are designed to observe and measure phenomena within our own universe, making it exceedingly difficult to access or establish contact with alternate realities. Some researchers speculate that if multiverses influence each other, there might be faint traces of their existence discernible through cosmic background radiation or anomalies within quantum mechanics. These hints could potentially point to overlapping characteristics or interactions, but this remains firmly in the realm of speculation and theory. The prospect of interacting with parallel universes poses further complexities. It could involve travel through dimensions or wormholes, concepts that currently reside in the theoretical domain. While science fiction often portrays these journeys as feasible, practical implementation faces substantial barriers from our current understanding of physics. The thought of encountering an alternate version of reality encourages profound exploration of existence and the universe, yet it leaves us contemplating whether these realms remain forever beyond our reach, or if advances in science could revolutionize our understanding of all that lies beyond the observable universe. The many worlds interpretation of quantum mechanics presents profound implications for our understanding of reality, existence, and the nature of observation. At its core, this interpretation suggests that every quantum event leads to the branching of the universe into multiple distinct realities, where all possible outcomes occur simultaneously. This challenges the conventional notion of a singular timeline, suggesting instead that our universe is just one of countless branches created by quantum decisions. Each time a particle behaves in a probabilistic manner, a new universe emerges, preserving all potential states. This framework profoundly alters our perception of choice and determinism. In the many worlds view, every decision we make spawns a new branch where different outcomes unfold. For instance, if one were to choose between two paths, there exist parallel universes where each possible choice is realized. This raises fascinating questions about fate and free will, as it suggests that every possibility is actualized somewhere in the multiverse, complicating our understanding of choice. Such a perspective evokes deep philosophical inquiries about the nature of consciousness and how we perceive our reality. Additionally, the many worlds interpretation emphasizes the significance of the observer in the quantum realm. Traditionally, quantum mechanics relies on wave function collapse, a process where probabilities resolve into a single outcome upon observation. However, in the many worlds scenario, it is the observer's consciousness that branches along with the universe, experiencing only one of the many outcomes. This redefines our role as observers, positioning us as participants in an ever-expanding cosmic tapestry of possibilities. Moreover, the many worlds interpretation prompts scientists to reconsider the nature of reality itself. Instead of viewing the universe as singular and objective, it can now be perceived as an intricate network of potentialities. This potentially shifts the focus of scientific inquiry towards a better understanding of quantum phenomena, and may even lead to new paradigms in theoretical physics. While the many worlds interpretation remains unproven and continues to spark debate among physicists, its implications compel us to rethink fundamental concepts of existence and invite us to explore the remarkable fabric of reality, where the extraordinary breadth of possibilities awaits discovery. The fascinating idea that alternate versions of ourselves might exist in parallel universes stems from the many worlds interpretation of quantum mechanics. According to this interpretation, every decision or change at the quantum level can lead to branching realities, creating multiple outcomes and, consequently, different versions of ourselves. Every choice we make, no matter how trivial, could spawn a unique path in a separate universe where a different outcome occurs. This leads to a multitude of scenarios exploring how our lives might have unfolded differently based on varying decisions. For instance, consider a simple decision like choosing a career. In one universe, you might have pursued a career in the arts, while in another, you may have chosen a path in science. Each of these decisions, along with countless others, could result in entirely different lives shaped by the paths diverged upon those choices. Thus, there could potentially be infinite iterations of ourselves exploring different identities, experiences, and destinies across various realities. This concept raises intriguing philosophical questions about identity and existence. If alternate versions of ourselves are indeed real, what does that mean for our understanding of self? Each version could reflect different traits, experiences, and opportunities, all coexisting in an intricate web of realities. The realization that alternate selves face distinct challenges and triumphs can deepen our appreciation for our own choices and the complexities of existence, provoking thoughts about regret, fate, and personal growth. While engaging in these musings invites wonder, it is essential to acknowledge the limitations of our current scientific understanding. The idea of interacting with alternate versions of ourselves or accessing parallel universes remains speculative. However, exploring these possibilities encourages us to reflect on the nature of reality and our choices, illuminating our lives against the backdrop of the infinite. This contemplation can inspire a greater understanding of who we are and the myriad potentialities that lie within and beyond our experiences. Cosmic strings are theoretical one-dimensional defects predicted by certain models in physics, notably in the context of string theory and field theory. They are envisioned as extremely thin, yet immensely dense, structures that can stretch across vast distances in the universe. Their unique properties suggest that they might have formed during the early moments of the universe, specifically in the rapid cooling phase following the Big Bang. As the universe expanded and cooled, different fields that were once unified began to separate, leading to the formation of these topological defects. The formation of cosmic strings is closely linked to symmetry breaking, a process in which a system that begins in a symmetric state ends up in an asymmetric state after undergoing certain changes. In the early universe, as it cooled, the fundamental forces and particles cooled and transitioned from a high-energy unified state into the distinct forces we observe today. This rapid phase transition might have created regions of space that exhibited different field values, leading to the creation of cosmic strings as the fields settled into their new energy states. These strings possess intriguing properties, including the potential to warp space-time around them. If they exist, cosmic strings could have significant gravitational effects on surrounding matter, influencing the formation of galaxies and clusters. The presence of cosmic strings might generate gravitational waves as they move and interact, offering a means to detect them indirectly through observational astrophysics. Though no direct evidence has yet confirmed the existence of cosmic strings, they remain an important area of theoretical research. The search for these exotic structures could provide valuable insights into the conditions of the early universe and the fundamental aspects of cosmic evolution. understanding cosmic strings deepens our knowledge of the universe's infancy and the complex interplay of physical forces that shaped our reality into what we experience today. Cosmic strings, if they exist, might indeed provide explanations for various unexplained phenomena observed in the universe. The unique properties of these one-dimensional defects could influence cosmic structures and the behavior of matter and energy in ways that challenge our current understanding of physics. One area of interest is their potential role in the formation of cosmic structures, such as galaxies and galaxy clusters, which appears to exhibit complex alignment and distribution patterns that have yet to be fully understood. The gravitational effects of cosmic strings, given their immense density and tension, could warp space-time around them. As a result, they might act as gravitational lenses, bending the path of light from distant objects. This effect could lead to observable distortions in the shapes of galaxies or clusters of galaxies, contributing to phenomena like the cosmic web, where matter seems thread-like rather than uniformly distributed. If cosmic strings are indeed present, their influence could help explain certain irregularities observed in gravity lensing and the distribution of cosmic mass. Additionally, cosmic strings could also be linked to primordial gravitational waves. As they move through the universe, interactions between cosmic strings could create ripples in space-time, potentially detectable through experiments designed to observe such waves. The patterns and spectra of these gravitational waves might provide evidence for cosmic strings and offer insights into early universe dynamics, particularly concerning phase transitions and symmetry breaking. Though research into cosmic strings is ongoing, the implications of their existence could shift our understanding of fundamental physics. If these structures account for some of the unexplained phenomena we observe today, they would deepen our appreciation for the intricate web of forces that shape the universe. They encourage further investigation into the relationship between cosmic evolution and the exotic possibilities that fill the cosmos, motivating scientists to explore realms of uncertainty where extraordinary discoveries may lie. In addition to cosmic strings, several other types of topological defects are theorized to exist in the universe, each arising from different symmetry-breaking processes during the early moments of cosmic evolution. Among them are monopoles, domain walls, and textures, each with unique characteristics and potential implications for our understanding of the universe. Monopoles are hypothetical magnetic monopoles, a concept suggesting that magnetic charges could exist independently, unlike the dipoles we commonly observe, which have both a north and a south pole. In various grand unified theories, magnetic monopoles could have formed during phase transitions in the early universe. Their existence would support certain theoretical models in particle physics and could provide insights into fundamental forces and symmetries. Detecting these elusive particles would revolutionize our understanding of electromagnetism and magnetism itself. Domain walls are another type of topological defect that could form due to symmetry breaking within a scalar field. These two-dimensional defects arise when different regions of a field settle into distinct vacuum states, leading to boundaries that separate them. Domain walls can have significant effects on the universe's large-scale structure. If they exist, they might influence the distribution of matter or play a role in the evolution of the cosmic microwave background radiation. Textures represent a third category of topological defects, which are more complex arrangements of the fields in the early universe. They arise from fields that have multiple possible vacuum states and can exhibit a tangled, more three-dimensional structure. Textures might inherently connect different regions of space through their intricate topology. While their exact implications remain less understood, they could affect cosmic evolution and influence processes such as galaxy formation or the dynamics of cosmic inflation. Each of these topological defects presents a unique perspective on the early universe's conditions and the fundamental forces that govern it. As scientists explore these concepts further, they have the potential to reveal more about the universe's formation, the nature of matter, and the complexities of physical laws. The search for evidence of these defects could open new pathways in both theoretical and observational cosmology, deepening our grasp of the profound intricacies that shape the cosmos. Cosmic strings and other topological defects have the potential to significantly influence the structure and evolution of the universe in various ways. Their unique properties can alter gravitational dynamics, affect the distribution of matter, and even impact the formation of galaxies and cosmic structures. One of the primary ways these defects could affect the universe is through their gravitational effects. Cosmic strings, due to their high density and tension, create gravitational fields that can warp space-time, potentially bending the paths of nearby matter and light. This warping effect could lead to observable phenomena like gravitational lensing, where the light from distant galaxies or cosmic structures is distorted as it passes near a cosmic string. If such strings exist, they could delineate regions of space where the gravitational influence results in unusual clustering of matter, impacting the overall arrangement of galaxies and clusters throughout the universe. Such interactions could also facilitate the formation of large-scale structures by acting as seeds around which matter coalesces, leading to the formation of galaxies and clusters. Topological defects like domain walls and textures may similarly influence the fabric of cosmic evolution. Domain walls, acting as boundaries between different field configurations, could affect the energy density in various regions of space, impacting the growth of structures in their vicinity. If domain walls are abundant, they may create regions of high density that attract matter, thereby assisting in the gravitational clumping necessary for structure formation. Textures, with their complex arrangements, could contribute dynamism to the cosmic landscape by facilitating energy fluctuations in the early universe, influencing inflationary processes and the subsequent large-scale structure. Moreover, the existence of these defect structures might help explain some of the irregularities and anisotropies observed in the cosmic microwave background radiation. The early universe's dynamics could have left imprints that we experience today, and analyzing these signatures may offer insight into the role of cosmic strings and other defects in shaping the universe as we know it. Thus, the exploration of cosmic strings and related topological defects could pave the way for a deeper understanding of the universe's history and the fundamental processes that have led to its current state, enhancing our comprehension of matter, energy, and the cosmos. As of now, there is no direct observational evidence confirming the existence of cosmic strings or other topological defects. However, scientists have not entirely dismissed their potential presence, and research continues to explore indirect ways to detect them. The search for cosmic strings and similar structures leans heavily on their theoretical implications and the observable phenomena associated with them. One promising avenue for indirect evidence lies in the study of gravitational waves. If cosmic strings exist, their interactions could generate unique patterns of gravitational waves, which scientists hope to detect using observatories like the Laser Interferometer Gravitational Wave Observatory. Observations of such waves might provide evidence of cosmic strings, particularly if they originate from dynamic interactions involving these structures. The distinctive signatures of gravitational waves linked to cosmic string interactions could help astronomers distinguish them from other sources of cosmic turbulence. Cosmic microwave background radiation also serves as a potential observational window for these defects. Variations in temperature and polarization patterns observed in this background radiation might offer insights into the early universe's conditions. If cosmic strings or other topological defects influence the expansion and development of the universe, their presence could leave detectable imprints in this ancient radiation. Scientists analyze data from the Planck satellite and other observatories to search for anomalies that could suggest the influence of such structures. Additionally, observational astronomers have looked to how the large-scale structure of the universe appears. The clustering and distribution of galaxies may contain patterns that argue for the past presence of topological defects. Such irregularities could relate to gravitational interactions created by cosmic strings or domain walls. These patterns provide a secondary line of inquiry, suggesting a more complex universe than current models account for. While direct evidence remains elusive, ongoing research, intricate observational efforts, and advancements in both theoretical and experimental physics continue to seek insights into cosmic strings and topological defects. Each study contributes to our understanding of the universe's structure and evolution, propelling the search for these enigmatic features towards new horizons. The apparent imbalance between matter and antimatter in the observable universe, known as baryon asymmetry, is one of the most profound and unresolved questions in modern cosmology and particle physics. According to the fundamental laws of physics, when particles interact, they usually produce equal amounts of matter and antimatter. However, observations reveal that the universe is overwhelmingly dominated by matter, with very little antimatter detectable. Several theories attempt to explain this discrepancy, but no single explanation has garnered unanimous support. One leading hypothesis is based on the concept of baryogenesis, which refers to the processes that led to the excess of baryons or matter particles over antibaryons. This process might involve conditions in the early universe different from those in current experiments. Specifically, the evolution of the universe shortly after the Big Bang could have favored reactions that produced more matter than antimatter. Certain particle interactions might have occurred in ways that preferentially generated baryons under specific conditions, such as those involving high temperatures and energy levels. A crucial aspect of baryogenesis theories is the requirement of violating certain symmetries in particle physics, particularly charge conjugation and parity, which together form a combined symmetry called C and CP symmetry. Under these symmetries, the laws of physics should ideally treat matter and antimatter equally. However, experiments have indicated a violation of CP symmetry in specific decays of certain particles, such as kaons and B mesons, suggesting that the slight differences in behavior between matter and antimatter could lead to an abundance of matter over antimatter in the universe. Another line of investigation involves various mechanisms proposed to account for the asymmetry, including electroweak baryogenesis and the creation of leptogenesis. These mechanisms suggest that processes involving neutrinos or other fundamental particles could lead to a net excess of matter. As these theories evolve, they often rely on untested scenarios involving physics beyond the standard model, which describes the fundamental particles and their interactions. Though considerable progress has been made in understanding the imbalance of matter and antimatter, a comprehensive resolution remains elusive. Ongoing experimental initiatives, such as those at particle accelerators and neutrino observatories, aim to probe the fundamental properties of particles to uncover clues about this baryon asymmetry. By continuing to explore these questions, researchers hope to gain insights into the very nature of our universe and the underlying mechanisms that have shaped its composition. The matter-antimatter asymmetry in the early universe is attributed to several proposed mechanisms, collectively trying to explain why we observe an overwhelming abundance of matter compared to antimatter. One of the central ideas revolves around a concept known as baryogenesis, which refers to the processes that led to an excess of baryons, the particles that make up matter, over antibaryons, their antimatter counterparts. Several specific mechanisms within this framework have been theorized to account for this asymmetry. One significant theory is electroweak baryogenesis, which suggests that during the electroweak phase transition in the cooling universe, conditions emerged that allowed for the violation of certain symmetries, particularly charge conjugation and parity, known collectively as CP violation. This CP violation could create situations where collisions or decays of particles lead to preferential production of baryons over antibaryons. This mechanism relies on the behavior of particles and fields in the early cosmos, where extreme temperatures and densities could influence the rates of various processes. Another proposed mechanism is known as leptogenesis, which indicates that processes involving neutrinos might have played a pivotal role in creating the matter-antimatter asymmetry. In this scenario, the decay of heavy particles known as right-handed neutrinos could produce an imbalance between leptons, which include neutrinos and their charged counterparts, and antileptons, which could subsequently lead to a surplus of baryons through interactions governed by the standard model of particle physics. This line of reasoning connects the behavior of neutrinos to the larger picture of particle interactions in the universe. Furthermore, some models involve various forms of strong CP violation, with theoretical frameworks suggesting the existence of additional particles or forces not accounted for in the current understanding of particle physics. Some mechanisms hypothesize that in the early universe's rapidly changing conditions, new physics could have emerged, creating the necessary imbalances while interacting with other forces. The precise cause of the matter-antimatter asymmetry remains an open question and is an important area of research in physics. Experiments probing high-energy collisions at particle accelerators seek to uncover potential CP violation, while astrophysical observations of cosmic phenomena might provide insights into the early conditions of the universe. The quest to understand this asymmetry not only seeks to explain our existence in a matter-dominated universe, but also aims to unravel the deeper properties of the fundamental forces and particles that govern the cosmos. 2. The idea that there could be regions of the universe dominated by antimatter is a fascinating concept that stems from our understanding of particle physics and cosmology. While current observations indicate that the observable universe is predominantly composed of matter, it remains theoretically possible that antimatter could exist in separate regions or pockets beyond what we have detected. However, the implications of such regions raise substantial questions regarding the nature of the universe and the interactions between matter and antimatter. If regions of antimatter do exist, they would likely be isolated from matter to avoid annihilation. When matter and antimatter come into contact, they destroy each other in a burst of energy, producing gamma rays. This annihilation process would make mixed regions of matter and antimatter highly unstable, leading to fierce radiation that would be detectable. Hence, if large areas of the universe were dominated by antimatter, we would expect to observe substantial signals of annihilation at the boundaries where matter meets antimatter. The creation of antimatter regions might theoretically be supported by models of the early universe. During the Big Bang and subsequent rapid expansion, the universe could have had localized fluctuations that led to the creation of isolated regions of antimatter. However, the distribution of matter and antimatter would have had to be significantly asymmetric to avoid mutual annihilation, allowing for stable zones that retained their antimatter properties. To date, extensive observations of cosmic background radiation and the large-scale structure of the universe have found no evidence for significant regions of antimatter. Cosmic rays have been studied as well, looking for signs of the interaction between matter and antimatter. Yet results have consistently indicated a matter-dominated universe. Some cosmological models predict that if antimatter regions do exist, they would likely be far from our observable horizon, making it difficult for us to detect them directly. The search for antimatter and the possibility of antimatter regions remains an area of scientific interest. Understanding this could deepen our comprehension of fundamental physics and the early conditions of the universe. It forces us to grapple with significant questions about the nature of reality, existence, and the cosmic balance between matter and antimatter, ultimately challenging our understanding of the universe as a cohesive entity. If matter and antimatter were to collide on a large scale, the consequences would be extraordinarily dramatic and catastrophic. The interaction between these two forms of matter leads to mutual annihilation, a process in which particles of matter and their corresponding antiparticles convert their mass into energy according to Einstein's famous equation E equals mc squared. When a particle and its antiparticle collide, they annihilate each other, resulting in the release of high-energy photons, typically in the form of gamma rays. On a large scale, such a collision could produce immense amounts of energy. For example, if a quantity of antimatter equivalent to the mass of a small object, such as a kilogram, were to meet with an equal amount of matter, the resulting explosion would yield energy equivalent to that released by a significant nuclear detonation. The annihilation process generates gamma rays that reach high frequencies, which are among the most energetic forms of light, leading to intense bursts of radiation that can be lethal and can traverse vast distances in space. This violent interaction would produce not only gamma rays, but also a variety of other subatomic particles, including pions, muons, and even neutrinos. The resulting energy release could create a cascade of subsequent interactions that might influence nearby matter and energy, leading to a larger area of effect. The radiation produced would present serious dangers to any nearby objects, potentially resulting in destruction over a considerable distance. In a theoretical context, an environment dominated by matter-antimatter collisions could lead to highly energetic regions in space that might replicate phenomena observed in extreme astrophysical events, such as gamma-ray bursts. These bursts are among the most powerful explosions in the universe, linked to rapid processes involving matter and energy in collapsing stars or other extreme conditions. While these large-scale annihilation events are not observed in our current universe, given the apparent dominance of matter, the theoretical exploration of such reactions emphasizes the unique characteristics and extraordinary energy dynamics inherent in the fabric of the universe. The study of matter-antimatter interactions deepens our understanding of the fundamental forces and particles that govern existence, captivating our imagination with the sheer power held within these enigmatic interactions. Antimatter, the mysterious counterpart to regular matter, holds fascinating possibilities for practical applications in science and technology. One of the most discussed applications is in the realm of medical imaging, particularly through positron emission tomography, often referred to as PET scans. This imaging technique utilizes positrons, which are the antimatter counterparts to electrons, to detect and visualize metabolic processes in the body. By injecting a small amount of a radioactive substance that emits positrons, healthcare professionals can create detailed images, aiding significantly in the diagnosis and monitoring of diseases such as cancer. Another promising area is in the development of advanced propulsion systems for space travel. The concept of antimatter propulsion is rooted in the tremendous energy release that occurs when matter and antimatter meet, resulting in near-complete conversion of mass to energy. If harnessed effectively, antimatter could revolutionize space exploration, offering engines that could theoretically propel spacecraft at speeds unattainable with current technologies. The challenges remain significant, primarily surrounding the production and storage of antimatter, which are currently limited and prohibitively expensive. Antimatter also finds its niche in fundamental physics research. Scientists utilize antimatter to explore the fundamental symmetries of the universe. Experiments at facilities like CERN are aimed at understanding why the universe is predominantly composed of matter, despite equal amounts of matter and antimatter being created in the Big Bang. This research has the potential to unlock new chapters in our understanding of the universe's workings, contributing to our foundational knowledge of cosmology. Finally, there is ongoing research into using antimatter as a potential source of energy, although this is still largely theoretical. The energy density of antimatter is unparalleled, leading scientists to consider its feasibility as a future energy solution. While practical applications are still far from realization, the potential of antimatter continues to captivate the scientific community and beyond, pushing the boundaries of what we know about our universe. The Fermi paradox presents a compelling question in the search for extraterrestrial life. If the universe is so vast and old, teeming with countless stars and planets, where is everyone? This paradox is named after physicist Enrico Fermi, who famously posed this question during a conversation in the 1950s. The dilemma arises from the apparent contradiction between the high probability of intelligent extraterrestrial civilizations and the lack of any evidence of their existence or contact with us. One implication of the Fermi paradox is that intelligent life may be extraordinarily rare in the universe. Factors such as the emergence of life, the development of intelligence, and the technological advancement required for interstellar communication could be so improbable that they occur only rarely, perhaps even limited to Earth. This viewpoint suggests that while microbial life may be common, complex, intelligent civilizations are exceedingly uncommon, leading to a vast silent cosmos. Alternatively, the paradox raises the possibility that advanced civilizations do exist but choose not to communicate or make their presence known. Many theories speculate that these civilizations might be following a policy of non-interference, akin to a cosmic prime directive, allowing developing societies to evolve without external influence. Another intriguing thought is the hypothesis that we might be living in a simulated reality where interstellar communication is a controlled variable. Additionally, some scenarios suggest that technological civilizations might be short-lived due to self-destruction through warfare, environmental collapse, or other existential risks. If civilizations tend to extinguish themselves before becoming capable of interstellar travel or communication, this would explain the silence we observe. Each of these interpretations of the Fermi paradox contributes to our understanding of the potential existence of alien life and the intricate dynamics that may govern its development throughout the cosmos. The Great Silence refers to the remarkable absence of evidence for extraterrestrial civilizations despite the vast number of stars and potentially habitable planets in the universe. Several theories have emerged to explain this phenomenon, each offering intriguing insights into our search for alien life. One prominent explanation hinges on the idea that intelligent life may be exceedingly rare. While the universe is home to countless stars and planets, the conditions necessary for life to emerge, and particularly for intelligent life to develop, could be so intricate and specific that they occur only under very particular circumstances. This line of reasoning suggests that while microbial life may be common across the cosmos, complex civilizations capable of technology and communication may be a rarity. Another possibility is the self-destruction hypothesis, which posits that advanced civilizations might tend to extinguish themselves shortly after developing technology capable of interstellar communication. Factors such as nuclear warfare, environmental degradation, or uncontrolled artificial intelligence could lead to civilizations collapsing before they have the chance to reach out or travel to other stars. If this scenario plays out frequently, it would create a galaxy filled with potential but silent worlds. The idea of the zoo hypothesis also provides a compelling explanation for the Great Silence. This theory posits that extraterrestrial civilizations are aware of us but deliberately choose not to make contact, opting instead to observe humanity as we evolve. According to this view, much like zookeepers protecting the animals in their care, advanced civilizations might adhere to a form of ethical non-interference, allowing us to develop without outside influence. Additionally, the technological singularity hypothesis suggests that civilizations may evolve into forms of intelligence beyond human comprehension, leading them to communicate in ways we cannot currently detect or understand. As technological capabilities advance, these civilizations might become so different from their origins that their presence or communications become unrecognizable to us. Each of these theories adds depth to the conversation about why, in a universe filled with potential life, we still find ourselves in the Great Silence. The Great Filter hypothesis offers a thought-provoking framework for understanding the absence of evidence for extraterrestrial life. It suggests that at some critical point in the evolutionary process, there is a highly improbable step that prevents civilizations from emerging or surviving. This filter could be behind us, meaning that while many planets may host simple life forms, the subsequent leap to intelligent, technologically advanced civilizations, is exceedingly rare. Alternatively, the filter could lie ahead of us, suggesting that even if intelligent life does emerge, it is unlikely to endure long enough to make contact. One common interpretation is that the Great Filter might occur at the transition from simple life to complex multicellular organisms. This step could be incredibly challenging, leading to the conclusion that while microbial life is abundant in the universe, intelligent life is not. If this initial filter exists, it could underpin why we observe a dearth of signals from other civilizations. They might simply not be able to make that leap. On the other hand, if the Great Filter lies in our future, it raises serious concerns about the sustainability of advanced civilizations. Climate change, nuclear threats, and other self-destructive tendencies might act as obstacles that prevent intelligent societies from surviving long enough to explore the galaxy or communicate with others. This interpretation suggests that many civilizations may reach a technological peak, but subsequently collapse, resulting in the quiet cosmos we experience. The Great Filter hypothesis stimulates deep philosophical considerations about our existence. It forces us to ponder not only the improbability of our own technological survival, but also the broader implications for life elsewhere in the universe. Understanding where the filter may lie gives us valuable insights into the nature of life, the risks faced by civilizations, and what our future might hold as we navigate our own technological progression. The question of whether we are the only advanced civilization in the galaxy or even the universe leads to a rich tapestry of speculation and scientific inquiry. Estimating the chances of our singularity involves numerous factors, including the vastness of the cosmos, the frequency of suitable planetary conditions, and the various steps necessary for intelligent life to evolve. The Milky Way galaxy alone contains hundreds of billions of stars, many of which likely host planets within their habitable zones. Current estimates suggest there could be at least several billion planets where life-supporting conditions may exist. This raises the probability of life emerging somewhere in this vast expanse. However, the leap from simple life forms to intelligent, technologically advanced civilizations remains a complex and poorly understood process, which significantly complicates the calculation of our uniqueness. Another important consideration involves the potential stages of development along the evolutionary path. Numerous filters, such as the emergence of complex multicellular organisms, the rise of intelligence, and technological advancement, suggest that many critical hurdles must be passed for a civilization to achieve the capability for interstellar communication. Each of these steps incorporates elements of chance, leading to uncertainty around how many civilizations might actually succeed. Furthermore, even if other advanced civilizations do exist, various factors could prevent us from discovering them. These include the vast distances between stars, the short time frames in which civilizations remain detectable, and the possibility that other intelligent species may use communication methods we do not yet understand. Consequently, while statistical models and astronomical observations support the potential for many civilizations, definitive evidence of others remains elusive, leaving the question of our uniqueness tantalizingly open-ended. Resolving the Fermi paradox would significantly impact our understanding of humanity's place in the universe and could reshape our philosophical, scientific, and cultural perspectives. If we were to discover evidence of extraterrestrial civilizations, it would affirm that intelligent life is a common outcome in the cosmos, challenging the notion that humans are uniquely special. This revelation might encourage a sense of interconnectedness with the universe, prompting us to view ourselves as part of a broader galactic community. Conversely, if the resolution indicated that we are indeed the only advanced civilization, it could instill a profound sense of responsibility. Such a finding might motivate humanity to consider its role as stewards of Earth and potential pioneers in a silent universe. This awareness could foster a deeper commitment to sustainability and ethical behavior, recognizing that our choices may influence not just our future, but the legacy we leave for any future intelligences that might arise. The implications of either scenario would also extend to scientific pursuits. Discovering other civilizations could ignite a new wave of collaborative research, driving humanity to explore the nature of these civilizations, their technologies, and their philosophies. Conversely, confirming our isolated status might redirect scientific focus towards understanding the factors that enable life to flourish or falter, informing how we approach our own survival and evolution. Ultimately, resolving the Fermi paradox could significantly redefine humanity's narrative within the universe, whether positioning us as one of many or highlighting our solitary existence amidst a cosmic expanse. This profound understanding would undeniably influence not only how we see ourselves, but also how we aspire to engage with one another and the universe at large. Magnetars are a special class of neutron stars characterized by their incredibly strong magnetic fields, which are among the most powerful observed in the universe. A typical neutron star is already a dense remnant of a supernova explosion, formed when a massive star exhausts its nuclear fuel and collapses under its own gravity. However, a magnetar takes this phenomenon a step further, featuring a magnetic field that can exceed 1,000 trillion Gauss. For context, this is about 1 trillion times stronger than the magnetic field of Earth. The intense magnetic fields of magnetars play a crucial role in their behavior and properties. These fields can influence the star's surface, causing it to emit bursts of high-energy radiation, particularly in the form of gamma rays and X-rays. This emission occurs through processes linked to the magnetic field, which can result in dramatic outbursts and flares. In fact, magnetars are known for their remarkable and unpredictable bursts of energy that can last for seconds, releasing as much energy as the sun emits over a period of millions of years. In comparison to other types of stars, magnetars stand out for their unique characteristics. Regular neutron stars do not possess magnetic fields as extreme as those of magnetars, and they exhibit different behaviors such as pulsars, which rotate rapidly and emit beams of radiation. While pulsars rely on their rapid spin and moderate magnetic fields to create periodic signals, magnetars are dominated by their magnetic forces, leading to different forms of radiation and dynamic behavior. The life cycle of a magnetar is also noteworthy. They are believed to form in the same manner as standard neutron stars, but are often thought to evolve more rapidly, with their magnetic fields weakening over time, ultimately becoming less active. Understanding magnetars not only challenges our concepts of stellar evolution and magnetic fields, but also provides insights into the extreme physical conditions of the universe, illustrating the diverse phenomena made possible by the laws of physics. Quark stars are intriguing theoretical entities that may exist in the realm of astrophysics. They are proposed to be a type of compact star formed under extreme conditions that break down protons and neutrons into their constituent quarks, which are fundamental particles. Unlike neutron stars, which consist primarily of tightly packed neutrons, quark stars would be composed mainly of a dense form of quark matter. This exotic state of matter arises when nuclear matter is compressed to such high densities that individual nucleons lose their identities and merge to form a new phase of matter. The existence of quark stars is supported by theoretical models, although no direct evidence has yet been found. They occupy a unique position in the spectrum of stellar remnants. For instance, their properties would lie between those of neutron stars and black holes. Quark stars could have different mass and radius characteristics than their neutron star counterparts, possibly allowing them to be distinguished through their gravitational waves or electromagnetic signals. Several factors contribute to the ongoing debate about their existence. One possibility is that quark stars could form in extreme environments, such as during the collapse of a supernova or in the aftermath of neutron star collisions. Such events may create the necessary conditions for the transition to quark matter to occur. Additionally, quark stars might exhibit behaviors not seen in neutron stars, such as unique thermal emissions or specific gravitational wave signatures, which could help identify them if they exist. While current observations have not definitively confirmed the existence of quark stars, the ongoing exploration of pulsars, neutron star collisions, and gravitational wave detections continues to provide valuable data. The scientific community remains engaged in both theoretical and observational studies to explore the possible existence of these exotic stars. If proven to exist, quark stars would challenge our understanding of fundamental physics and the behavior of matter under extreme conditions, deepening our knowledge of the universe's diversity. Starquakes are intriguing phenomena observed on neutron stars, specifically in those that exhibit crustal disruptions similar to earthquakes on Earth. These seismic events are believed to occur in the star's outer crust, which consists of a solid layer of atomic nuclei and electrons. The extreme conditions within neutron stars, such as intense gravitational forces and rapid rotation, create a highly complex environment where even minor disturbances can lead to significant disturbances in the crust. The mechanism behind starquakes is primarily linked to the immense pressures and temperatures present in these stellar remnants. Neutron stars are extraordinarily dense, with material packed so tightly that a sugar cube-sized amount would weigh as much as several mountain ranges. Under such intense conditions, the crust can experience stress due to the gradual accumulation of strain over time, akin to tectonic plates slowly moving along fault lines. When the stress at a critical point exceeds the strength of the crust, a sudden release of energy occurs, resulting in a starquake. These events are often associated with what's known as glitches, which are sudden increases in the rotation speed of a neutron star. After a starquake, a neutron star may exhibit a temporary increase in rotational frequency followed by a gradual slowdown. The released energy from a starquake can also produce observable effects in other parts of the star, including changes in temperature and shifts in X-ray emissions. Such observations are vital for astrophysicists, as they can provide insights into the internal structure and behavior of neutron stars. Starquakes contribute to our understanding of the extreme states of matter found in neutron stars, as well as the complex interplay between their crust, core, and magnetic fields. Continued observations of these remarkable events help shed light on the underlying physics governing neutron stars and deepen our appreciation for the diverse phenomena present in the universe. The disappearance of stars without a supernova event, while rare, can occur under specific circumstances, typically involving a process known as the star quenching. One way this phenomenon manifests is through the rapid consumption of a star's fuel sources, where it exhausts its nuclear fuel at a significantly faster rate than typical stellar evolution would suggest. When a massive star runs out of hydrogen and helium, it can enter a phase of instability, contracting under gravity without producing the explosive outward pressures needed to trigger a supernova. Another scenario involves the possibility of a star falling into a black hole. If a massive star orbits very close to a black hole, gravitational forces may cause it to lose mass over time. The intense gravitational pull can strip away the outer layers of the star steadily, causing it to become fainter and drenching it in tidal forces that ultimately lead to its disappearance. In such cases, the star's material is not lost in a spectacular explosion. Instead, it is drawn in and assimilated by the black hole. Moreover, certain intermediate mass stars may experience a loss of mass due to strong stellar winds, which can lead to a state where a significant portion of the star's material is expelled. If a star loses enough mass, it may not have enough material left to undergo a typical supernova event. Instead, it can simply fade away as its outer layers are stripped, leaving only a remnant core, which might eventually turn into a white dwarf. Lastly, there's the phenomenon of stellar mergers, where two stars in a binary system collide and merge, leading to complex and varied outcomes. Depending on the masses involved and the dynamics of the merger, the star may undergo significant alterations, including potentially vanishing from sight if the explosion is sufficiently quiet or contained. Each of these scenarios highlights the complex and dynamic processes governing stellar life cycles, revealing that the universe holds many surprises beyond conventional explosive endings. Tabby's star, officially known as KIC 86628, has captured the imagination of astronomers and the public alike due to its unusual and irregular dimming behavior. Discovered by the Kepler Space Telescope, the star exhibits significant fluctuations in brightness that do not fit the expected patterns associated with standard stars. Over several years of observation, researchers noted that Tabby's star could dim by as much as 20%, which is a substantial amount and raises intriguing questions about the underlying causes. One of the primary hypotheses involves the presence of a swarm of exocomets. This idea suggests that a series of comets may be orbiting the star, with their occasional transits across its face resulting in the observed dimming events. As these icy bodies pass in front of the star, they block out a noticeable portion of its light. While this scenario could account for some dimming events, it does not entirely explain the irregular and varying nature of the brightness fluctuations. Another speculative explanation ties into the possibility of a massive artificial structure like a Dyson sphere built by an advanced civilization. This theory, while tantalizing, is considered far less likely given the lack of concrete evidence supporting the presence of such technology. However, the very notion of an alien megastructure around Tabby's star reflects the star's mysterious nature and the eagerness of scientists to explore all possible explanations. Further investigation into Tabby's star continues, including ongoing monitoring and improved observational techniques to determine the precise reasons behind its unique dimming patterns. As astronomers gather more data, they hope to unravel the mysteries of this enigmatic star, contributing to our broader understanding of stellar behavior and the potential for diverse phenomena in the universe. The quest to explain Tabby's star serves as a reminder of the vast unknowns that still await discovery within our cosmos. Gravitational waves are ripples in space-time, caused by the acceleration of massive objects, such as colliding black holes or neutron stars. Predicted by Albert Einstein in 1915 as a part of his general theory of relativity, these waves are generated when massive celestial bodies distort the fabric of space-time around them. When two dense objects orbit each other and eventually merge, they produce powerful gravitational waves that propagate outward at the speed of light, carrying information about their origins and the extreme conditions involved in such catastrophic events. The detection of gravitational waves represents a groundbreaking advancement in astrophysics, offering a new window into the universe that complements traditional electromagnetic observations such as light, radio, and X-rays. Gravitational waves provide insights into phenomena that are often invisible or undetectable through conventional methods. For instance, while black holes cannot be observed directly in the traditional sense, the merging of these objects creates gravitational waves that can be detected by instruments like the Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO. By observing these waves, scientists can gather data about the properties of the cosmic events that generated them, such as the masses and spins of the merging objects, their distance from Earth, and the dynamics of the merger process. This direct measurement of gravitational waves opens the door to studying highly energetic and transient events in the universe, enhancing our understanding of fundamental physics and the behavior of matter in extreme conditions. As more gravitational wave events are detected, researchers hope to explore a variety of astrophysical phenomena, from the formation and evolution of black holes to the behavior of neutron stars, and even the early moments of the universe itself. Gravitational waves have paved the way for an entirely new field of astronomy, known as gravitational wave astronomy, allowing us to observe and understand aspects of the cosmos that we were previously unable to access. The gravitational waves detected so far have yielded remarkable insights into some of the most violent and energetic processes in the universe. fundamentally transforming our understanding of astrophysics. The detection of signals from merging black holes and neutron stars has provided crucial data about their properties, such as their masses and spins. These measurements help researchers refine their models of stellar evolution and gain a clearer understanding of the life cycles of stars, from their birth to their explosive deaths. One of the most significant findings from gravitational wave observations has been the confirmation of the existence of binary black hole systems. Many of the detected mergers involve pairs of black holes swirling around each other before ultimately colliding. Analysis of these events has not only revealed the range of black hole masses in the universe, but also indicated that black holes can form in a variety of ways, suggesting diverse pathways in their formation and evolution. Interestingly, some detected black holes appear to be heavier than previously thought possible, challenging existing theories about their formation. In addition to black hole mergers, the detection of gravitational waves from colliding neutron stars has opened a new chapter in astrophysics. For example, the event known as GW171017 marked a significant milestone in multi-messenger astronomy, as it was observed coincidentally with electromagnetic signals across the spectrum, including gamma rays and visible light. This event provided valuable information about the production of heavy elements such as gold and platinum formed during the merger, thereby linking gravitational wave astronomy to the origin of these elements in the universe. Furthermore, the study of gravitational waves offers a unique glimpse into the fundamental laws of physics, including testing aspects of general relativity under extreme conditions. As more gravitational wave events are detected and analyzed, researchers will continue to gather information that could lead to better models of the universe's underlying structure and the nature of dark matter and dark energy. Overall, gravitational waves have fundamentally expanded our cosmic toolkit, allowing us to probe the universe in ways previously thought impossible. Gravitational waves hold significant promise for advancing our understanding of dark matter and dark energy, two of the universe's most enigmatic components. While gravitational waves primarily emanate from events involving massive celestial bodies, the unique information they carry can indirectly illuminate various aspects of the cosmos, including the properties and effects of these mysterious entities. One way gravitational waves could aid in understanding dark matter is through their interactions with massive objects. As these waves propagate through space, they could potentially be influenced by the gravitational effects of dark matter, which behaves differently from ordinary matter. By analyzing how gravitational waves are affected when passing through regions of dark matter concentration, researchers may be able to glean insights into the distribution and properties of dark matter itself. This would enhance our knowledge of how dark matter interacts with visible matter in the universe. Regarding dark energy, which is believed to drive the accelerated expansion of the universe, gravitational waves could provide clues about the expansion history. Observations of gravitational waves from distant cosmic events, such as merging neutron stars or black holes, can serve as standard candles, similar to how supernovae are used. By measuring the distance to these events and their redshift, scientists can study the rate of expansion over time, which may help to shed light on the nature of dark energy and how it influences the cosmos. Furthermore, as detection techniques improve and more gravitational wave events are catalogued, the correlation between gravitational wave observations and large-scale structures in the universe can reveal critical information on how dark energy and dark matter shape the cosmic web. This could deepen our understanding of the universe's evolution and the interplay between these mysterious forces. Ultimately, while gravitational waves may not directly unveil the secrets of dark matter and dark energy, they offer a unique avenue for indirect observation and investigation. As our gravitational wave astronomy advances, researchers hope to utilize these phenomena to piece together the complex puzzle of the universe's composition and the fundamental forces driving its behavior. A variety of cosmic events are capable of producing detectable gravitational waves, each stemming from the dynamics of massive objects and their interactions in the universe. In addition to the well-known events of merging black holes and neutron stars, several other scenarios could generate these elusive waves. One significant source of gravitational waves is the merger of massive stars. When two very large stars spiral together, they can emit gravitational waves leading up to their collision. As they approach each other, their gravitational interaction intensifies, producing a series of waves that would be detectable by advanced observatories, particularly if the stars are in close orbit, leading to a merger into a single entity, often resulting in a black hole or a more massive neutron star. Supernova explosions, which mark the death throes of massive stars, are another potential source of gravitational waves. When a star undergoes core collapse, the sudden release of energy and the asymmetrical explosion can set off gravitational waves. However, detecting these waves is challenging because such events are relatively short-lived and occur at vast distances. Additionally, the collision and merger of white dwarfs can result in the release of gravitational waves. When two white dwarfs orbit each other closely and eventually merge, the event could produce a significant gravitational wave signal. Such interactions might be detectable, particularly if they occur in binary systems that are relatively nearby. Furthermore, pulsars, rapidly rotating neutron stars that emit beams of radiation, can create gravitational waves if they are in binary systems with other celestial bodies, or even if they have slight asymmetries in their shape. The ongoing interaction with another massive object can produce periodic gravitational waves detectable by observatories. Lastly, primordial gravitational waves generated during the inflationary period of the universe, shortly after the Big Bang, represent a theoretical possibility. Although detecting these waves would require highly sensitive technology, their study could provide invaluable insights into the very early universe and the fundamental physics at play. As the field of gravitational wave astronomy evolves, scientists will continue to hunt for signals from these and potentially other cosmic events, expanding our understanding of the universe and providing insights into the processes that shaped its structure. Future gravitational wave detectors promise to revolutionize our understanding of the universe in ways we are only beginning to grasp. Currently, gravitational waves serve as ripples in space-time produced by dramatic astrophysical events such as the merging of black holes and neutron stars. As these detectors become more advanced, they will be capable of capturing waves from a broader range of sources and events, thus enriching our cosmic knowledge. One significant advancement includes the ability to detect weaker signals from events farther away in the universe. This could allow scientists to observe the mergers of black holes that occurred billions of years ago. By studying these ancient events, researchers will glean insights into the formation and evolution of galaxies, stars, and black holes over cosmic time. This deeper understanding could reveal how structure and matter in the universe evolved since the Big Bang. Additionally, as detectors improve in sensitivity and resolution, they will not only capture the gravitational waves produced during cataclysmic events, but also potentially observe gravitational waves from the early universe. These signals could provide crucial information about the conditions that existed during the first moments after the Big Bang, leading us to a better understanding of the origins of our universe. Moreover, with future detectors operating in space, astronomers will be able to explore a wider frequency range of gravitational waves. This capability would enable the observation of events that cannot be detected from the ground, such as certain types of phenomena involving supermassive black holes or exotic astrophysical processes. Each new wave detected will help us piece together the complex narrative of the cosmos and reveal how it works on both macroscopic and microscopic scales. This transformative research will likely ignite new theories and concepts that could change our understanding of fundamental physics. The universe's structure resembles a vast cosmic web made up of filaments, walls, and voids due to gravitational interactions shaping its distribution of matter over billions of years. Early in its history, shortly after the Big Bang, matter was distributed quite uniformly. However, slight variations in density led to gravitational pulls that began to draw matter together. These initial clumps of matter attracted more material, resulting in the development of larger structures. As gravity continued to exert its influence, matter coalesced to form dense regions called filaments, which interconnect like the strands of a web. These filaments contain galaxies and galaxy clusters, which are some of the universe's most important structures. Between these filaments exist vast, nearly empty spaces known as voids. They can be several hundred million light-years across and contain very little matter, yet their presence helps define the pattern of the universe's large-scale structure. The tendency of matter to clump together is influenced by dark matter, an invisible substance that does not emit light but has mass and therefore exerts gravitational forces. Dark matter plays a critical role in the universe's organization, forming a scaffold upon which visible matter accumulates. Its gravitational pull aids in the formation of filaments and clusters, essentially guiding where galaxies eventually form and reside. Additionally, the expansion of the universe affects this structure as it not only stretches the distances between these cosmic filaments and voids, but also influences how they evolve over time. The interplay between gravity, dark matter, and cosmic expansion leads to this intricate and beautiful arrangement of the universe's large-scale structure, shaping the very fabric of the cosmos we observe today. The Great Wall structures in the universe refer to colossal superclusters of galaxies that form some of the largest known cosmic features. These structures are not mere patterns. They are vast networks that consist of many galaxy clusters, filaments, and voids intricately interconnected by gravitational forces. The term wall highlights their immense scale and the fact that they create boundaries in the cosmic web, separating the empty voids that exist between them. One of the most well-known examples is the Sloan Great Wall, which spans approximately 100 million light-years in length. Discovered in the early 21st century, this structure is composed of numerous galaxy clusters and is a part of the larger framework that populates the universe with rich areas of concentrated matter. The existence of such walls challenges earlier notions of a homogeneous universe, emphasizing instead that matter is distributed in a highly interconnected and non-uniform manner. The formation of these great walls can be traced back to the dynamics of gravitational collapse. As the universe expanded after the Big Bang, slight variations in density led to gravitational attraction, causing matter to aggregate into these massive structures over billions of years. Understanding the formation and evolution of the Great Walls can provide immense insights into the nature of dark matter, the distribution of galaxies, and the overall history of the universe. Studying these great walls allows astronomers to understand the large-scale structure of the universe better. Observations of the walls reveal information about galaxy formation, the influence of dark energy, and the complex interactions that govern cosmic evolution. As researchers continue to explore these colossal structures, they glean valuable knowledge about the forces shaping our universe, ultimately painting a fuller picture of the cosmos and its grand architecture. The large-scale structure of the universe has undergone a remarkable evolution since its inception. After the Big Bang, which took place approximately 13.8 billion years ago, the universe began as a hot, dense plasma. As it expanded and cooled, matter began to condense due to gravitational forces. Initially, this process created small fluctuations in density, which served as the seeds for all future cosmic structures. Over time, these small fluctuations grew larger through the influence of gravity, causing matter to clump together. Regions of higher density attracted more materials, setting off a chain reaction that led to the formation of the first stars and galaxies. This early period, known as the Cosmic Dark Ages, eventually ended when the first stars ignited, reionizing the surrounding gas and leading to the second phase of cosmic evolution. This era marked an explosion of star formation, which helped to further distribute heavy elements throughout the universe. As galaxies interacted and merged, they formed larger structures known as galaxy clusters. Over billions of years, the gravitational pull of these clusters created filaments that interconnected and formed a cosmic web. As the universe continued to expand, some areas became densely packed with galaxies, while others evolved into massive voids, regions with minimal galaxy presence. This network of filaments, walls, and voids outlines the large-scale structure we observe today. Current observations reveal that the evolution of the universe's structure is still ongoing. Dark energy is believed to be playing a critical role in its accelerated expansion. This expansion affects how galaxies and clusters move apart, influencing the dynamics of the cosmic web. The interplay between gravity, dark matter, and dark energy shapes the ongoing narrative of the universe's large-scale architecture, providing astronomers and cosmologists with rich data to understand the cosmos's past and its future trajectory. The large-scale structure of the universe is a profound source of information that can reveal essential insights about the fundamental properties of the cosmos. By studying how matter is distributed across vast distances, scientists can glean hints about the underlying physical laws that govern the universe's behavior. One of the most significant pieces of information relates to the nature and amount of dark matter, a mysterious substance that constitutes roughly 27% of the total matter-energy content of the universe. The distribution of galaxies and galaxy clusters reflects the gravitational effects of dark matter. Observations show that structures tend to form along filaments and in dense regions where dark matter is abundant. Analyzing these patterns helps scientists understand both the characteristics of dark matter, such as its influence on galaxy formation, and its role in the universe's expansion. The way that galaxies cluster together also points to the effects of gravity in shaping the cosmos, offering clues about the mass and strength of the gravitational forces at play. Furthermore, the large-scale structure is intimately linked to the expansion of the universe, which is driven by dark energy, a force that works against gravity. The rate of expansion helps to inform models of the universe's evolution. By observing how structures grow and change over time, researchers can better quantify the effects of dark energy and refine their understanding of its nature, whether it is a constant force or varies over time. The large-scale structure serves as a cosmic canvas, illustrating the interplay between various forces like gravity and dark energy, and showcasing the distribution of different types of matter. Through detailed observations and simulations, scientists can explore fundamental questions about the universe, including its ultimate fate, the fundamental nature of its constituents, and the physics that governs reality itself. While the large-scale structure of the universe adheres to a general framework of cosmic evolution, there are indeed anomalies and unexplained features that challenge our understanding and raise intriguing questions. One notable example is the cold spot found in the cosmic microwave background radiation, which is the afterglow of the Big Bang. This region appears unusually devoid of temperature fluctuations compared to other areas, suggesting a significant deficit of galaxy formation or an unexpected influence during the early phases of the universe. Another striking anomaly is the unexpected alignment of certain galaxy clusters and superclusters. Some of these structures appear to exhibit alignment with the cosmic microwave background, hinting at potential underlying physics that is not yet fully understood. This phenomenon could imply that there are ancient cosmic events or forces at play that are influencing the distribution and orientation of galaxies across vast distances in ways that current models do not predict. There are also perplexing observations regarding large voids. While voids are regions with significantly fewer galaxies, some of them are larger than current simulations suggest should exist. These supervoids pique interest as they may contain mysterious components or profound insights into dark energy and the universe's expansion dynamics. Their sheer size and behavior contradict some aspects of conventional cosmological models. Finally, the structure of the universe also raises questions about homogeneity and isotropy, which are foundational assumptions in cosmology. Certain observations, such as the distribution of galaxies and their clustering patterns, hint at potential inconsistencies in the uniformity of matter in the universe. These anomalies invite scientists to explore and potentially revise existing theories, enriching the dialogue and investigation within cosmological research. Each unexplained feature prompts further inquiry and experimentation, emphasizing the dynamic nature of our understanding of the cosmos. The theory of cosmic inflation posits that the universe underwent an exponential expansion during the first moments following the Big Bang, approximately between 10 to the negative 32nd and 10 to the negative 29th seconds after the event. This rapid inflationary phase would have expanded the universe by a factor of at least 10 to the 27th, smoothing out any initial irregularities and leading to a nearly homogeneous and isotropic universe. This theory addresses several puzzles in cosmology, including the flatness problem, the horizon problem, and the absence of magnetic monopoles. One key piece of evidence supporting the theory of inflation comes from observations of the cosmic microwave background radiation. Detailed measurements from missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have shown temperature fluctuations in the microwave background that correspond to quantum fluctuations in the density of matter during the inflationary period. These fluctuations eventually grew into the large-scale structure of the universe, such as galaxies and galaxy clusters, which we observe today. Additionally, the theory of inflation provides an explanation for the observed uniformity of the cosmic microwave background across vast distances. Without inflation, regions of the universe now separated by billions of light-years would not have had the chance to exchange information or energy due to the finite speed of light, leading to significant temperature differences. The inflationary model, however, allows for these regions to have once been in thermal equilibrium before expanding rapidly and becoming disconnected. Finally, the presence of gravitational waves predicted to be generated during inflation offers another aspect of potential evidence. These primordial gravitational waves, if detected, would provide a unique signature of the inflationary epoch and further bolster the theory. Current experiments, such as the BICEP and the upcoming LIGO observations, aim to investigate this aspect of inflation. Altogether, the theory of cosmic inflation elegantly ties together multiple observations and offers a compelling framework for understanding the early universe's dynamics. Cosmic inflation played a crucial role in shaping the early universe and the framework of its structure. During the initial moments after the Big Bang, the rapid exponential expansion caused by inflation smoothed out any irregularities in the distribution of matter and energy. This process allowed for an almost uniform universe, facilitating the conditions necessary for the consistent structure we observe today. With this increased uniformity, inflation provided a foundation for the subsequent fluctuations that would be essential for the formation of galaxies and other cosmic structures. As the universe experienced inflation, tiny quantum fluctuations in the energy field generated regions of slightly varying density. These density fluctuations, once inflated, became the seeds from which all subsequent large-scale structures would develop. After inflation ended, the universe transitioned into a more gradual expansion, allowing these fluctuations to grow under the influence of gravity. Over billions of years, the gravitational pull of these denser regions attracted more matter, leading to the formation of stars, galaxies, and galaxy clusters. Inflation also contributed significantly to the homogeneity of the universe on large scales. By stretching any existing variations in density beyond perceptible levels, inflation erased potential irregularities that could have complicated or hindered the growth of structures. It allowed regions of the cosmos that are now separated by vast distances to have once been in close contact, hence enabling them to share similar properties despite the current uniform distribution. Furthermore, the inflationary theory also helps explain the flatness of the universe. The rapid expansion would have flattened any curvature, leading to the almost perfect spatial geometry observed today. This characteristic supports the notion that the universe is critically balanced between an open and closed fate, reinforcing the prevailing idea that we live in a flat universe that continues to evolve under the influence of dark energy. Thus, inflation is a cornerstone in our understanding of the universe's early days and how its intricate structure took shape. The end of the inflationary epoch is believed to have been triggered by the rapid decay of the inflation field, which caused the energy driving inflation to convert into ordinary matter and radiation. This process is often referred to as reheating. During inflation, a scalar field, often called the inflaton field, dominated the universe and provided the energy necessary for the exponential expansion. When the dynamics of this field changed, it led to a rapid decrease in its energy density. As the inflaton field decayed, it transferred its energy into particles, creating a hot, dense state filled with a mix of elementary particles. This event marked the transition from inflation to what is referred to as the hot Big Bang phase. Following reheating, the universe was filled with a high-energy plasma composed of quarks, electrons, neutrinos, and other fundamental particles interacting at incredibly high temperatures. After the inflaton field ended and the universe transitioned to the hot Big Bang phase, it continued to expand and cool. As the temperature dropped, quarks began to form protons and neutrons, and these baryonic particles eventually combined to make light nuclei during a period known as Big Bang nucleosynthesis, which occurred within the first few minutes. Elements such as hydrogen, helium, and small traces of lithium were synthesized during this time, laying the groundwork for the chemical elements that would ultimately form stars and galaxies. As the universe expanded and cooled further, it eventually entered the epoch known as recombination, roughly 380,000 years after the Big Bang. During recombination, electrons combined with protons to form neutral hydrogen atoms. This event allowed photons to travel freely through space, resulting in the release of the cosmic microwave background radiation that we detect today. This rich tapestry of events initiated the evolution of the universe into its current state, leading to the formation of large-scale structures through gravitational attraction over billions of years. The possibility of multiple periods of inflation in the early universe is a topic of significant interest and debate among cosmologists. While the standard theory of inflation suggests a single, rapid inflationary event, some models propose that there could have been multiple inflationary episodes, each with its characteristics and consequences for the structure of the universe. One of the motivations for considering multiple periods of inflation comes from certain theoretical frameworks, such as chaotic inflation and eternal inflation. Chaotic inflation suggests that inflation can occur repeatedly in different regions of space due to variations in the inflaton field. In this scenario, while some regions of the universe undergo a brief inflationary phase, others could remain in a state of inflation for extended periods, leading to a multiverse concept where many bubble universes exist, each with its physical properties. Eternal inflation posits that the inflaton field does not settle into a stable state everywhere simultaneously. Instead, certain regions of space can stop inflating while others continue to undergo inflation indefinitely. This asymmetrical behavior implies that the universe could be characterized by an infinite number of inflationary bubbles, giving rise to a multiverse where each bubble could have different properties, laws of physics, and space-time structures. The implications of recurring inflation are profound. If true, they could provide explanations for the observed uniformity of the cosmic microwave background, while also accounting for the observed anisotropies within it. Multiple inflationary events might also help to clarify some of the observed large-scale structures and the distribution of galaxies throughout the cosmos. While the concept of multiple inflationary periods remains speculative, researchers are actively exploring both observational and theoretical avenues to test these ideas. Current and future observational data, such as measurements of the cosmic microwave background and potential primordial gravitational waves, could offer insights that help distinguish between single and multiple inflation scenarios, ultimately deepening our understanding of the universe's early evolution. Cosmic inflation has profound implications for the ultimate fate of the universe, influencing how we understand its long-term evolution and structure. The rapid expansion of space during the inflationary epoch not only set the stage for the uniformity observed in the cosmic microwave background, but also affected the dynamics of matter, dark energy, and overall cosmic expansion. One key implication of inflation is its relationship with the concept of dark energy, which is believed to drive the universe's accelerated expansion. The inflationary model suggests that after the initial inflationary phase, the universe transitioned into a more stable, gradually expanding state. If dark energy continues to dominate the energy density of the universe will likely continue to expand indefinitely. This outcome is often referred to as the Big Freeze, or heat death, where galaxies move farther apart and the universe cools over trillions of years. Stars will eventually exhaust their nuclear fuel, and galaxies may fade into darkness, leading to a cold and sparse universe. On the other hand, if inflation leads to a multiverse scenario, each bubble universe might follow its distinct path of development. In this view, different regions could experience different rates of expansion or variations in physical laws, making the ultimate fate of our universe one among many possibilities. This aligns with certain interpretations of quantum mechanics and cosmology, where infinitely diverse outcomes may emerge depending on the initial conditions of inflation. Additionally, some inflationary models suggest cyclic behavior where the universe could undergo multiple phases of expansion and contraction. In this scenario, the universe might periodically collapse, leading to a big crunch, followed by another inflationary phase. While this concept challenges our current understanding of cosmic expansion, it suggests that the universe's fate could be more dynamic than a simple linear progression toward a cold, empty outcome. Ultimately, the implications of cosmic inflation on the fate of the universe continue to be an active area of research. As observational techniques and theoretical models evolve, we may gain insights into whether our universe is on a path to eternal expansion, a cyclic future, or an entirely different scenario that awaits discovery. Each possibility underscores the intricate relationship between the initial conditions set by inflation and the cosmic evolution that follows. At a fundamental level, gravity is understood through the framework of the theory of general relativity, proposed by Albert Einstein in the early 20th century. According to this theory, gravity is not merely a force acting at a distance as previously thought, but rather a curvature of space-time caused by the presence of mass. Massive objects like planets, stars, and galaxies warp the surrounding fabric of space-time, creating a well that influences the motion of other objects within that curved space-time. This means that when an object, such as a planet, moves through space, it is not directly attracted to another object through a force in the classical sense. Instead, it follows a path determined by the geometry of the space-time around it. This concept is often illustrated by imagining a heavy ball placed on a stretched rubber sheet. The ball creates a depression that affects smaller objects placed nearby, causing them to roll toward the larger mass. This curved geometry explains how planets orbit stars, how galaxies interact, and even how light bends around massive objects, a phenomenon known as gravitational lensing. While general relativity provides profound insights into how gravity functions on large scales, there remains a quest to understand gravity at the quantum level, particularly in the context of quantum mechanics. At these scales, the behavior of particles is governed by quantum fields and probabilities. Physicists theorize that a particle called the graviton would mediate gravitational interactions in a quantum framework, similar to how photons mediate electromagnetic interactions. However, The graviton remains hypothetical, as a unifying theory that seamlessly integrates gravity with quantum mechanics has yet to be developed. Current research in theoretical physics aims to reconcile these two frameworks. Approaches such as string theory and loop quantum gravity propose different models to describe gravity's fundamental nature. Understanding gravity at the most fundamental level not only enhances our grasp of the universe's workings, but also has implications for our comprehension of black holes, the behavior of galaxies, and the nature of space-time itself. As scientists pursue answers to these profound questions, the quest to understand gravity may ultimately unveil deeper layers of reality within the cosmos. The relationship between gravity and the curvature of spacetime lies at the heart of Einstein's theory of general relativity. In this framework, gravity is not simply viewed as an attractive force acting between masses, as was proposed by Isaac Newton. Instead, gravity is described as the effect of the curvature of spacetime created by objects with mass. This reimagining of gravity fundamentally alters our understanding of how massive objects interact with one another and how they influence the paths of other objects, including light. When mass is present, it alters the geometry of spacetime surrounding it due to its gravitational influence. This curvature can be visualized as a fabric that bends in the presence of heavy objects. For example, if a star or a planet is situated in this fabric, it causes a dent or depression that affects nearby objects. When a smaller mass, such as a satellite or another planet, approaches this curved region, it will move along the paths dictated by the curvature, much like a marble rolling in a shallow bowl. This movement appears as an orbital motion, such as that of planets around a star. The extent to which spacetime is curved varies with the mass of the object and the density of the surrounding area. Denser masses create stronger curvature, leading to stronger gravitational effects. Light, which travels along the straightest possible paths in spacetime called geodesics, is also affected by this curvature. When light passes near a massive object, such as a galaxy, it will bend due to the spacetime distortion caused by that object's mass, a phenomenon observed in gravitational lensing. By describing gravity in terms of spacetime curvature, general relativity provides a comprehensive understanding of various gravitational phenomena, including the precession of planetary orbits, the behavior of objects in strong gravitational fields, and the effects seen near black holes. This relationship underscores the interconnectedness of mass, space, and time, revealing that gravity is an integral feature of the universe's underlying structure. The equations governing these principles, known as the Einstein field equations, continue to be a cornerstone for understanding cosmological events and the fundamental nature of reality. The concept of extra dimensions of space beyond the familiar three spatial dimensions is a fascinating aspect of modern theoretical physics. Certain advanced theories, such as string theory and various models of higher dimensional spacetime, suggest that additional dimensions could exist but remain hidden from our direct observation. These theories posit that the fundamental constituents of the universe, subatomic particles, are actually tiny, vibrating strings or membranes that require more than 3 dimensions to fully describe their behavior. String theory, for example, typically requires 10 or 11 dimensions for mathematical consistency, where the additional dimensions may be compactified or curled up so tightly that they are imperceptible at everyday scales. In this framework, the extra dimensions can influence the properties of particles, such as their mass and charge, by altering the way strings vibrate in those dimensions. The implications of such extra dimensions could provide answers to open questions in physics and unify the fundamental forces, including gravity, electromagnetism, and the strong and weak nuclear forces. The idea of extra dimensions can also help explain phenomena like gravity's relative weakness compared to other fundamental forces. If gravity propagates through these additional dimensions, while the other forces remain confined to the familiar three-dimensional space, it could account for gravity's apparent weakness at macroscopic scales. This perspective is known as the brain world scenario, implying that our observable universe could be a three-dimensional brain embedded in a higher dimensional space. While these theories are compelling and mathematically intriguing, direct experimental evidence for extra dimensions remains elusive. Researchers are conducting high-energy physics experiments, such as those at the Large Hadron Collider, to search for signs of extra dimensions, such as deviations from the expected behavior of particles or the production of mini-black holes. Additionally, cosmological observations and gravitational wave studies may offer hints about the properties of the universe that could point to the existence of extra dimensions. The exploration of extra dimensions poses deep philosophical questions about the nature of reality and our perception of the universe. If proven true, the existence of these dimensions would significantly reshape our understanding of fundamental physics and the architecture of the cosmos, leading to a deeper comprehension of the fabric of reality itself. Quantum gravity aims to bridge the gap between general relativity and quantum mechanics, two pillars of modern physics that describe the universe at vastly different scales. General relativity effectively describes the gravitational interactions of massive objects in a smooth, continuous space-time, while quantum mechanics manages the behavior of particles at the atomic and subatomic levels, where the laws of probability govern interactions. Despite their successes within their domains, these theories have shown incompatibilities in phenomena such as black holes and the very early universe, where both gravity and quantum effects are significant. One of the primary approaches to quantum gravity involves the idea of unifying these two frameworks through a theory that treats spacetime itself as a dynamic, quantized entity. In this context, spacetime may not be a smooth canvas as depicted in general relativity, but rather a foamy structure composed of discrete units at the Planck scale. Researchers have proposed various models such as loop quantum gravity and string theory to capture this idea. Loop quantum gravity, for instance, posits that spacetime is quantized into tiny loops or networks, allowing gravitational fields to have discrete values and providing a framework to describe gravity without relying solely on the classical geometric interpretation of spacetime. String theory also seeks to reconcile these two realms by positing that the fundamental building blocks of the universe are one-dimensional strings instead of zero-dimensional particles. These strings vibrate at different frequencies, with their specific vibrational patterns corresponding to different particles. String theory inherently incorporates gravity through the presence of gravitons, the hypothetical quantum particles that mediate gravitational interactions, suggesting a way to incorporate gravitational effects within a quantum framework. A successful theory of quantum gravity could resolve several key issues that arise when merging general relativity and quantum mechanics. For example, it might provide insights into the nature of singularities found in black holes, where the laws of physics seem to break down. Additionally, it could clarify how information is preserved in black hole scenarios, potentially offering solutions to the black hole information paradox. Ultimately, the development of a coherent quantum gravity theory has the potential to enrich our understanding of the universe's fundamental workings and to reveal a unified description of all fundamental forces, gravity, electromagnetism, and nuclear interactions, enabling physicists to explore deeper questions about the nature of reality, space, and time. As researchers continue to explore these concepts, the quest for quantum gravity remains one of the most profound and exciting challenges in contemporary physics. The holographic principle presents a fascinating perspective on the nature of spacetime, suggesting that our three-dimensional universe may fundamentally be a projection of information encoded on a two-dimensional surface. This idea challenges traditional notions of space and time, positing that the information contained within a volume of space is not merely stored within that volume, but instead correlates with data residing on its boundary. This perspective shifts how we understand gravity, black holes, and ultimately, the fabric of the cosmos. One of the most striking implications of the holographic principle is its connection to black holes. According to this principle, the information about what falls into a black hole is not lost. Instead, it is theorized to be encoded on the event horizon, the boundary around the black hole. This idea aligns with the outcomes from quantum mechanics, suggesting that information cannot simply vanish, which introduces profound implications for theories about the fate of matter and energy in our universe. Furthermore, this principle implies that space and time, as we understand them in our everyday experiences, might be emergent phenomena rather than fundamental constructs. Within this framework, space-time could be viewed as a byproduct of underlying informational processes, reshaping our understanding of reality itself. It challenges scientists to rethink the building blocks of the universe, indicating that at a deep level, the fabric of reality may be more akin to a vast cosmic database. The exploration of the holographic principle encourages ongoing research in theoretical physics and cosmology, pushing the boundaries of our knowledge about the dynamics of the universe. Such groundbreaking theories inspire questions about the very essence of existence, reshaping how we visualize the interplay of matter, energy, and the structure of space-time itself. The fate of the universe hinges on a delicate interplay of various factors, primarily its expansion rate and the total amount of matter and energy it contains. Observations suggest that the universe has been expanding since the Big Bang, and more recently, studies have revealed that this expansion is accelerating due to a mysterious force known as dark energy. This phenomenon raises the possibility that the universe could continue to expand indefinitely. If the current trend of accelerating expansion continues, the universe may enter an era known as the Big Freeze. In this scenario, galaxies would drift increasingly apart, stars would burn out, and eventually, the universe would become dark, cold, and devoid of significant activity. This long-term outcome would mark an end to any semblance of structured cosmic phenomena, leading to a vast silent expanse where only isolated remnants of stars might exist. Conversely, there is the possibility of a scenario known as the Big Crunch. This would occur if the gravitational pull of all the matter in the universe was strong enough to overcome the force of dark energy, ultimately halting the expansion and reversing it. In such a case, everything could collapse back into a singularity, reminiscent of the state of the universe before the Big Bang. However, current observations indicate that dark energy is dominating the universe's dynamics, making the Big Crunch seem less likely. The ongoing debate about the ultimate fate of the universe is not just a question of physics, but also one of philosophy. As researchers continue to uncover the properties of dark energy and other cosmic components, our understanding of the universe's destiny evolves. The question of whether the universe will persist in its expansion or undergo a drastic reversal remains one of the most intriguing enigmas in cosmology. As we peer into the very long-term future of the universe, spanning trillions of years ahead, we encounter some profound and intriguing scenarios shaped by our current understanding of cosmic dynamics. Assuming the prevailing trend of accelerating expansion driven by dark energy continues, the universe is likely to evolve into a state often referred to as the Big Freeze. In this future, galaxies would drift endlessly apart, resulting in a cosmos marked by vast emptiness and isolation. In this far-off reality, the life cycles of stars would unfold dramatically. Most stars will eventually exhaust their nuclear fuel and gradually fade, leaving behind remnants such as white dwarfs, neutron stars, or black holes. Over immense timescales, even these remnants will cool and dim, ultimately contributing to a dark universe devoid of active stellar processes. The galaxies themselves will become increasingly sparse, and cosmic structures will be rendered nearly invisible against the backdrop of an expansive dark sky. Completely separate from the fate of stars, black holes, those enigmatic regions of space-time with gravitational pull so strong that not even light can escape, would dominate the landscape. However, even black holes are not eternal. Over trillions of years, they are estimated to gradually evaporate through a process known as Hawking radiation, rendering them into nothingness. This emission of radiation means that even the most colossal black holes will eventually vanish, contributing to the chill of the cosmic environment. As time stretches into the unimaginable, the universe might end in a state referred to as heat death. This scenario envisions a universe where all energy is uniformly distributed, leading to a state of thermodynamic equilibrium. In such a world, there would be no significant changes or events, leaving an eerily quiet expanse. It is a thought-provoking future, evoking questions about the very nature of existence and the long-term meaning of cosmic evolution in a seemingly static and unchanging universe. The potential endings of the universe, characterized as the Big Rip and heat death, represent two contrasting scenarios shaped by the fundamental forces and energy dynamics at play in our cosmos. Each scenario offers a distinct picture of what could happen as time progresses, shaped primarily by the mysterious nature of dark energy, which is currently driving the universe's accelerated expansion. The Big Rip is a captivating theory that suggests a future where the expansion of the universe continues to accelerate uncontrollably. In this scenario, the force of dark energy becomes so dominant that it begins to overwhelm all other interactions, from the gravitational pull holding galaxies together to the forces that bind atoms. As the expansion rate increases, structures on every scale, from galaxy clusters down to individual stars and even the atoms themselves, would eventually be torn apart. This dramatic ending would unfold over a timeline that could span billions of years, culminating in a universe where everything is ripped asunder in a cataclysmic finale. On the other hand, the heat death scenario is grounded in the concept of thermodynamic equilibrium. Over an incredibly long timescale, as stars die and galaxies drift apart, the universe would reach a state where all energy is evenly spread. In this cold, dark future, there would be minimal activity, no stars shining, no life forms thriving, and a lack of interactions to create dynamic events. This universe would be stable but utterly devoid of structure or change, resembling an unlit theater after the final curtain has fallen. In contemplating which scenario is more plausible, current observations suggest that dark energy is indeed accelerating the universe's expansion. However, the nature of dark energy remains one of cosmology's most significant mysteries. Depending on how dark energy evolves over time, it could lead us down either the path to a big rip or toward a gradual heat death. As research continues, the questions surrounding these ultimate fates highlight the profound complexity of our universe and the forces that govern its destiny. The question of whether the universe is finite or infinite in extent poses a significant challenge for cosmologists and researchers. Both possibilities offer intriguing implications that shape our understanding of the cosmos. Current observations suggest that the universe is vast and may even appear flat based on measurements of cosmic microwave background radiation, but whether it extends infinitely or wraps back on itself remains an active area of investigation. If the universe is finite, it implies a defined volume of space with a limit to the extent of matter, energy, and the structures we observe. A finite universe could potentially be shaped like a higher dimensional sphere or similar geometric construct, allowing for a scenario where traveling far enough in one direction might ultimately lead one back to their starting point. Such a finite universe raises questions about its boundary, if it has one, and what lies beyond it. This possibility challenges our intuition, leading to considerations about the nature of existence and whether anything exists outside our universe. Conversely, an infinite universe suggests that space extends endlessly in all directions, filled with a potentially unending distribution of galaxies, stars, and interstellar matter. An infinite cosmos presents a radical perspective on reality. It would imply that no matter how far one travels, new regions of space remain to be discovered, each with possibly endless variations of cosmic phenomena. This notion resonates with the idea of infinite possibilities, where every combination of matter could exist somewhere in the vast expanse. The implications of a finite versus an infinite universe extend beyond mere measurements and geography. They influence philosophical questions regarding the nature of existence and our place within the cosmos. A finite universe might hint at a specific origin or endpoint, while an infinite one challenges concepts of singularity and the ultimate nature of reality. As scientists investigate this profound question, the quest for understanding highlights the interplay between observation, theory, and the fundamental nature of space and time itself. Based on current knowledge and observations in cosmology, several plausible scenarios emerge regarding the ultimate fate of the universe. Each of these scenarios hinges on the interplay between the expansion of the universe, dark energy, and the overall density of matter and energy in existence. One of the leading possibilities is the Big Freeze, which predicts that the universe will continue to expand at an accelerating rate. This scenario is driven primarily by dark energy, creating a future where galaxies drift apart, stars burn out, and matter becomes increasingly sparse. Eventually, the universe would enter a state of thermodynamic equilibrium, characterized by a gradual cooling over trillions of years. In this outcome, cosmic activity would decline, leading to a dark and empty universe where only remnants of stellar processes remain scattered across the void. In contrast, the Big Rip presents a more dramatic scenario. This hypothesis suggests that if dark energy continues to grow unchecked, it could eventually overpower all other forces in the universe. This would result in an exponential increase in the rate of expansion, potentially tearing apart galaxies, stars, planets, and even atoms. The universe would culminate in a final cataclysm, where all structural integrity is lost. As devastating as this fate may seem, it remains one of the speculative possibilities that arise from our understanding of dark energy. Another scenario is the Big Crunch. This outcome could occur if the density of matter in the universe is sufficient to halt its expansion, leading to gravitational forces ultimately pulling everything back together. In this condition, the universe would contract, culminating in a singularity akin to the initial state from which it originated. While current observations lean toward a continuing expansion, the dynamics of dark energy could change over time, making the Big Crunch a consideration for certain models of the universe. Each of these scenarios reflects the intricacies of cosmic evolution and the enigmatic nature of dark energy. As researchers continue to gather data and refine their theories, understanding the universe's ultimate fate holds the promise of uncovering deeper truths about the cosmos and our place within it. The origin of the Moon is primarily explained by the giant impact hypothesis, which posits that it formed from the debris resulting from a colossal collision between the early Earth and a Mars-sized body, often referred to as Theia. This cataclysmic event is believed to have occurred around 4.5 billion years ago, shortly after the formation of the solar system. Following this immense impact, a significant amount of material was ejected into orbit around Earth. Over time, this debris coalesced to form the Moon. The giant impact hypothesis accounts for several key characteristics of the Moon. The composition of lunar rocks, brought back by Apollo missions, shows similarities to Earth's materials, particularly in isotopic signatures. This evidence supports the idea that the Moon was formed from Earth's outer layers rather than originating from a separate body in the solar system. Additionally, the unique size ratio of the Moon to Earth further substantiates this theory. The Moon is relatively large compared to Earth compared to the sizes of other planetary moons in the solar system. Furthermore, simulations and computer models of the giant impact have revealed plausible conditions leading to the Moon's formation, including how the material could have settled into orbit around Earth. These models show that such a collision would have resulted in a molten state for both the Earth and the ejector, allowing for the amalgamation of materials that eventually cooled and solidified into the moon we see today. As the moon stabilized in its orbit, it engaged in processes such as differentiation, which shaped its internal structure, and volcanic activity, which created the vast basaltic plains known as Maria. Understanding the moon's origins not only sheds light on its history, but also offers insights into the early solar system's formation and the dynamic processes that influenced the development of planetary bodies. The stark contrast between the far side and the near side of the moon primarily arises from a phenomenon known as tidal locking. This occurs because the moon is gravitationally bound to Earth in such a way that it rotates on its axis in the same amount of time it takes to orbit our planet. As a result, the same side of the moon, the near side, always faces Earth, while the far side remains largely hidden from direct view. This unique situation has led to significant differences in geological features. The near side is characterized by large, smooth expanses called maria, formed by ancient volcanic activity. These dark basalt plains are the remnants of lava flows that filled impact basins, which were more prevalent on that side due to its exposure to Earth's gravitational influences. The near side also contains higher concentrations of lowland areas where these volcanic eruptions occurred, giving it a distinct appearance. In contrast, the far side of the moon features a heavily cratered landscape with fewer maria. The far side's surface is older and has not been subject to the same volcanic resurfacing that shaped the near side. Initially, it was thought to be an impenetrable mystery until the Soviet lunar missions in the 1960s and 70s provided the first images and data. These missions revealed a rugged terrain with many craters, as well as the presence of lunar highlands. 2. The difference in appearance also results from the moon's thinner crust on the near side, which allowed volcanic activity to occur more readily. The thickened crust on the far side has inhibited such activity, leading to the stark contrast in the geological history and surface features. This fascinating dichotomy enhances our understanding of the moon's evolution and the complex dynamics that govern the interactions between celestial bodies. The mysterious flashes of light observed on the moon, often referred to as transient lunar phenomena, have intrigued scientists and amateur astronomers alike for centuries. Various explanations have been proposed to account for these enigmatic events, although no single theory has been definitively proven. The flashes can occur in different forms, including brief illuminations and more prolonged glows, and they seem to happen randomly. One popular explanation for some of these flashes is related to the impact of micrometeorites. When tiny meteoroids collide with the lunar surface at high speeds, they can generate enough energy to produce short-lived bright flashes. These impacts are common due to the lack of atmosphere on the moon, which allows small objects to strike the surface without burning up first. The resulting explosions could create temporary luminance that observers on Earth might see as a flash. Another possibility is the reflection of sunlight off of the surface materials, or even the interaction of the lunar regolith, the moon's loose surface layer, with the sunlight. Shifting particles or changes in the surface's micron-sized details due to solar wind interactions or seismic activity could also create variations in brightness, leading to transient appearances of light. This phenomenon could be heightened during lunar eclipses or specific solar configurations. Additionally, some researchers have proposed that these flashes might be associated with gas emissions from the lunar surface. The moon, although geologically inactive compared to Earth, can still experience outgassing events where small amounts of gases escape from the interior. These releases could generate flashes due to the reactions with solar radiation or local environmental conditions. Despite multiple hypotheses, the exact cause of transient lunar phenomena remains largely unexplained. Ongoing observations and advancements in technology may eventually shed light on these intriguing occurrences, providing deeper insights into the lunar environment and the dynamic processes at play on our nearest celestial neighbor. The possibility of natural satellites orbiting Earth beyond the moon is an intriguing topic in celestial mechanics. While the Moon is the most significant and well-known natural satellite, astronomers have identified other objects that temporarily capture Earth's gravitational influence, albeit not in the same stable manner as the Moon. One notable example is the phenomenon of temporary satellites, often referred to as mini-moons. These are small asteroids that occasionally enter Earth's orbit, becoming temporary natural satellites for a period ranging from a few months to several years before they ultimately escape back into space. One such mini-moon, designated 2006 RH1, was discovered in 2006 and orbited Earth for approximately 11 months before drifting away. These temporary objects showcase how the gravitational pull of our planet can capture passing space debris, albeit only temporarily. Another fascinating aspect involves the existence of quasi-satellites, which are objects that orbit the Sun in a way that places them in a relative orbit with Earth. For example, an asteroid known as 1660012 Icarus follows an orbit that allows it to remain in close proximity to Earth for extended periods. Although these quasi-satellites do not technically orbit Earth, their orbital paths create the illusion that they are following our planet. However, the conditions necessary for a stable and long-term natural satellite like the Moon are quite unique. Factors such as size, mass, and a suitable distance from the planet make it challenging for other objects to achieve such a status. The Moon's large size relative to Earth and its resulting gravitational interactions play a significant role in stabilizing its orbit and influencing our planet's tides and axial tilt. While the potential for other stable natural satellites exists based on gravitational interactions, the Moon remains the dominant satellite of Earth. The search for temporary satellites and quasi-satellites continues, revealing the dynamic interplay of celestial bodies in the expanses of space surrounding our planet. Tabby's star, officially designated KIC 8725088, has captivated astronomers and enthusiasts alike due to its peculiar light patterns characterized by irregular and significant dimming. Located approximately 1,300 light-years away in the constellation Cygnus, Tabby's star was first observed as an anomaly in 2015, when data from the Kepler Space Telescope highlighted its unusual fluctuations in brightness. The irregular dimming of Tabby's star has led to numerous hypotheses about its nature. One of the most exciting yet speculative explanations is the possibility of a structure built by an advanced civilization, sometimes referred to as a Dyson sphere, that could cause significant light blockage as it orbited the star. However, this idea, while intriguing, lacks substantial evidence and is regarded as less likely by most scientists, who favor more natural explanations. The leading theories center around cosmic phenomena. One possibility is that the dimming is caused by a large cloud of dust or debris passing in front of the star, blocking its light intermittently. This would suggest that the star is surrounded by an environment rich in material that could scatter or absorb light. Another theory proposes that the star itself has intrinsic variability, possibly linked to stellar activity or pulsations, causing it to change its brightness irregularly. Moreover, some researchers have suggested the impact of companion objects such as comets or protoplanets, which could produce temporary obscuration as they travel across the line of sight between Earth and Tabby's star. The abundance of comets could explain some of the sporadic dimming events, leading to the idea that a large population of icy bodies might exist in orbit around the star. While the precise cause of Tabby's star's enigmatic dimming patterns remains unresolved, ongoing observations and research continue to shed light on this cosmic mystery. The pursuit to understand this star not only unveils the complexities of stellar behavior, but also highlights the rich diversity of the universe and our ever-evolving understanding of celestial phenomena. The nature of consciousness remains one of the most profound and debated questions in philosophy, neuroscience, and cosmology. Two primary perspectives emerge in this discourse: the idea that consciousness might be a fundamental property of the universe, or the notion that it emerges from the complexity of neural networks and systems. One perspective posits that consciousness is a fundamental aspect of reality, akin to space, time, and matter. This view suggests that consciousness could exist independently of physical systems, potentially permeating the cosmos in some capacity. Proponents of this theory might invoke concepts from quantum mechanics or various philosophical considerations, arguing that consciousness is intertwined with the fabric of the universe, perhaps even influencing phenomena at fundamental levels. This perspective is sometimes connected to panpsychism, which asserts that all matter might possess some form of consciousness or experience. On the other hand, the dominant view within neuroscience and psychology is that consciousness emerges from the intricate interplay of complex biological systems, particularly the brain. According to this perspective, consciousness arises from the interactions of neurons, synapses, and biochemical processes, creating a rich tapestry of information processing that gives rise to subjective experience. As our understanding of brain function advances through fields such as neurobiology and cognitive science, researchers compile evidence supporting the idea that consciousness arises as an emergent property of highly organized systems rather than being fundamental. This discussion adds layers of complexity when considering the implications of each perspective. If consciousness is fundamental, it may inform our understanding of existence, suggesting that awareness is an intrinsic quality of the universe that could extend beyond human experience. However, if it emerges from complexity, it highlights the importance of brain organization and evolutionary processes, emphasizing the unique nature of conscious beings in the cosmos. Understanding consciousness involves a multidimensional exploration that crosses the boundaries of science and philosophy. As researchers continue to grapple with this intricate question, the quest for insights into consciousness not only influences our grasp of the human experience, but also provokes deeper inquiries into the nature of reality itself. The notion that the universe itself could possess some form of consciousness invites profound philosophical and scientific discussions. This idea, often referred to as cosmic or universal consciousness, proposes that consciousness is not solely a phenomenon arising from complex life forms, but could be an intrinsic quality of the universe itself. Various perspectives and theories explore the implications of this hypothesis, though it remains highly speculative. One approach to understanding this concept is the philosophical framework of panpsychism, which suggests that consciousness might be a fundamental aspect of all entities, even those considered inanimate. From this standpoint, everything in the universe, from subatomic particles to vast cosmic structures, could possess some form of awareness or experience, albeit in vastly differing degrees. This perspective paints the universe as a network of interconnections, where consciousness weaves into the very fabric of reality, leading to the notion that collective consciousness could emerge from these myriad interactions. Another consideration comes from the interplay of complex systems and information processing. Some theorists posit that if consciousness arises from intricate networks as observed in neural systems, then larger systems, such as the universe, could display behaviors that mimic consciousness. This could be likened to the flow of information and organization seen in living systems, where complex behaviors may emerge from the dynamics of many interconnected parts working together. However, empirical evidence to support the idea of a universally conscious entity remains elusive. Unlike human consciousness, with its distinctive subjective awareness, the concept of cosmic consciousness lacks clear mechanisms or measurable attributes. Most contemporary scientific inquiry focuses on consciousness as an emergent property of biological systems, emphasizing the significance of physical structures like the brain in generating subjective experiences. As the debate continues, exploring whether the universe could be conscious or possess aspects of awareness challenges our understanding of existence and reality. It opens up philosophical inquiries about the nature of consciousness and our place within the cosmos, ultimately enriching discussions that bridge science and philosophy. The relationship between consciousness and quantum mechanics has been a topic of intrigue and debate among physicists, philosophers, and cognitive scientists. Some theorists propose that quantum mechanics may provide insights into the nature of consciousness, while others argue that consciousness arises independently of physical phenomena. This connection often centers around the fundamental principles of quantum mechanics and how they might correlate with conscious experience. A key area of exploration involves the concept of observation in quantum mechanics. In this framework, the act of measuring a quantum system appears to influence its behavior. For example, particles like electrons can exist in multiple states simultaneously, described by a wave function. However, once a measurement is made, the system seems to collapse into a single state. Some theorists, including physicist Eugene Wigner, have pondered whether conscious observation is a necessary component for this collapse to occur, suggesting that consciousness plays an essential role in determining the state of quantum systems. Another theory linking consciousness and quantum mechanics is known as orchestrated objective reduction, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. This hypothesis suggests that consciousness arises from quantum processes occurring within microtubules, structures in the brain's neurons. According to this view, these quantum events could create moments of conscious awareness or decision-making. However, this theory is met with skepticism in the scientific community due to the challenges of maintaining quantum coherence in the warm and noisy environment of the brain. Conversely, many scientists argue against a direct connection between consciousness and quantum mechanics, asserting that consciousness can be fully explained through classical neuroscience and cognitive processes. They maintain that, while quantum mechanics profoundly influences the behavior of particles at a subatomic level, it does not extend to the macroscopic realm where conscious experience occurs. Instead, they emphasize that consciousness is an emergent property of complex neural networks, independent of quantum phenomena. The interplay between consciousness and quantum mechanics remains a provocative inquiry, reflecting the complexities of both fields. As advancements in both neuroscience and quantum physics continue, understanding the nature of consciousness may evolve, potentially leading to new insights and reconceptualizations of reality itself. The existence of consciousness profoundly affects our understanding of the universe in several intriguing ways, intertwining philosophy, science, and metaphysics. By examining consciousness, we engage with fundamental questions about existence, reality, and the nature of perception itself. This exploration can lead to transformative implications for our worldview. One significant impact of consciousness on our understanding of the universe lies in the subjective nature of experience. Conscious beings perceive the universe through their distinct sensory frameworks, leading to a variety of interpretations of reality. This subjectivity highlights the complexity of how we obtain knowledge and understand phenomena, suggesting that consciousness adds a layer of intricacy to our comprehension of the cosmos. The exploration of consciousness prompts us to consider whether any semblance of reality exists independently of an observer, entering the realms of philosophical inquiry and quantum mechanics, where observation seems to play a crucial role. Additionally, consciousness invites questions about the nature of existence. If consciousness is seen as an emergent property or a fundamental aspect of reality, it could alter our perception of life, matter, and the universe at large. This might lead to theories that posit interconnectedness, with consciousness acting as a binding force in both living and non-living systems. Such perspectives can encourage a more holistic view of the universe, wherein conscious experience not only arises from, but also contributes to the fabric of reality. Furthermore, the search for understanding consciousness drives research in various fields, from neuroscience to astrophysics. As we seek to comprehend how consciousness arises, we often explore the boundaries of physical laws and philosophical implications. Scientific inquiries into consciousness may lead to breakthroughs in our understanding of cognition, leading to new insights about human behavior, artificial intelligence, and even the potential for consciousness beyond biological systems. The existence of consciousness shapes our exploration of the universe, prompting profound questions about the nature of reality, our place within the cosmos, and the interconnectedness of all things. As we delve deeper into the relationship between consciousness and the universe, such inquiries may ultimately lead to a richer and more nuanced understanding of existence itself. The connection between consciousness and the observer effect in quantum physics is a topic that has fascinated both scientists and philosophers. The observer effect refers to the phenomenon whereby the act of measuring or observing a quantum system can influence the state of that system. In quantum mechanics, particles exist in a superposition of states until a measurement is made, at which point they collapse into a specific state. This intriguing behavior has led some to speculate about the role of consciousness in the measurement process. One argument put forth by proponents of the consciousness observation link is that conscious awareness might play a critical role in determining the outcomes of quantum measurements. Some physicists, like Eugene Wigner, have posited that consciousness is necessary for the collapse of the wave function. According to this view, the mere presence of a conscious observer is what solidifies a quantum state from multiple possibilities into a single observable reality. This notion suggests that consciousness could be intertwined with fundamental processes at the quantum level, prompting philosophical questions about the relationship between mind and matter. However, many physicists and scholars contend that the observer effect does not require consciousness for its occurrence. They argue that the term observer in quantum mechanics refers to any interaction that causes a measurement. This can include various forms of detection not limited to conscious awareness. In this context, the act of measurement itself is sufficient to affect the quantum system, and consciousness may not be a necessary component. This interpretation aligns with the Copenhagen interpretation of quantum mechanics, which emphasizes the importance of measurement without delving into the role of the observer's consciousness. Additionally, alternative interpretations of quantum mechanics, such as the many worlds interpretation, further distance the role of consciousness from the observer effect. This interpretation suggests that all possible outcomes of a quantum event occur in a vast multiverse, eliminating the need for conscious observation to influence reality. While the connection between consciousness and the observer effect remains a tantalizing idea, the scientific consensus suggests a more nuanced understanding. The observer effect itself is a fundamental characteristic of quantum mechanics that does not inherently depend on consciousness, though it certainly raises interesting questions about the nature of reality, observation, and human experience within the framework of quantum physics. As research continues, our comprehension of this complex relationship may evolve, influencing both scientific and philosophical thought. The idea that our universe could be a simulation running on a cosmic computer has gained traction in both philosophical discourse and scientific discussions. This notion, often referred to as the simulation hypothesis, suggests that what we perceive as reality might be an artificial construct generated by a more advanced civilization, or even an advanced form of intelligence. The implications of this hypothesis are profound and are rooted in several foundational considerations. One of the driving arguments behind the simulation hypothesis comes from advancements in technology and computer simulations. As our own computational capabilities rapidly evolve, researchers and theorists point out that it is becoming increasingly feasible to create highly detailed, complex simulations of reality. If a civilization reaches a level of technological prowess far beyond our current understanding, it might effectively create simulacra of entire universes, including the intricate laws of physics and the experiences of conscious beings within them. Philosopher Nick Bostrom is well known for articulating a version of this hypothesis, suggesting that at least one of the following propositions must be true. Advanced civilizations are unlikely to run many simulations of their historical past. They go extinct before they are capable of doing so, or we are almost certainly living in a simulation. This framework raises intriguing questions about our understanding of existence and the nature of reality itself, prompting us to consider the implications of a simulated universe on concepts such as free will, identity, and the nature of consciousness. Critics of the simulation hypothesis argue that it comes without robust evidence and that it may be unfalsifiable. That is, it could be challenging to prove or disprove. Additionally, some philosophers contend that the idea does not necessarily add explanatory power to our existing understanding of reality, as it could merely push the question of what is real one step further back. While intriguing, the simulation hypothesis remains speculative and philosophical in nature. As we explore the universe through the lens of science, it ultimately invites deeper inquiries about the nature of consciousness, reality, and our place within a potentially larger cosmic framework. Whether or not we live in a simulation, the hypothesis encourages us to reflect on fundamental questions about existence and the essence of what it means to be conscious beings navigating a complex universe. The simulation hypothesis holds profound implications for our understanding of the nature of reality, challenging traditional concepts and inviting philosophical, scientific, and ethical inquiries. If we were to accept that our universe is a sophisticated simulation created by an advanced civilization, several key considerations emerge that could reshape our worldview. First, the simulation hypothesis raises questions about the nature of existence itself. If reality is a simulation, then what we perceive as physical laws and constants might not be fundamental truths, but rather algorithms or rules established by the creators of the simulation. This perspective encourages a re-evaluation of our understanding of physics, biology, and consciousness, suggesting that what we deem objective reality could be merely a meticulously crafted illusion. It prompts us to ask, what constitutes authenticity in an existence that might be simulated? Additionally, the hypothesis has implications for free will and agency. If our actions and decisions exist within a programmed framework, it challenges the notion of autonomy and the authenticity of our experiences. Such a scenario raises deep philosophical questions about determinism and whether we have true control over our lives or whether our choices are predetermined by the underlying code of the simulation. This notion could lead to existential crises or shifts in how we perceive moral responsibility. The simulation hypothesis also opens doors to discussions about the nature of consciousness. It invites inquiries into whether consciousness could be part of the simulation or an independent entity interacting with it. Some theorists speculate that if we are in a simulation, consciousness may not be confined to biological substrates, but could also be replicated digitally. This consideration could expand the boundaries of understanding consciousness in artificial intelligence and the implications of creating sentient beings based on synthetic frameworks. Ethical dilemmas arise from this hypothesis as well. If we are indeed part of a simulation, what responsibilities do the creators, if they exist, have towards us? This raises questions about the ethics of simulation design and the treatment of sentient beings within it. Furthermore, if we discover ways to manipulate or alter the simulation, the moral implications of such actions could lead to significant debates regarding the rights of conscious entities within the simulated framework. Ultimately, the simulation hypothesis challenges our fundamental understanding of reality. By posing questions that probe the nature of existence, free will, consciousness, and morality, it encourages a deeper examination of what it means to exist, pushing the boundaries of both scientific inquiry and philosophical exploration. Testing whether we are living in a simulated universe is a complex challenge that ventures into philosophical, scientific, and technological realms. While the idea of being in a simulation is speculative, some scientists and theorists have proposed methods to explore this possibility through various avenues of inquiry. One approach involves searching for anomalies or glitches in the laws of physics that could indicate underlying computational limits in a simulated environment. For instance, if reality operates under specific rules akin to a computer program, there might be observable phenomena that behave inconsistently with our current understanding of physics. Researchers could examine areas such as quantum mechanics or cosmic phenomena for irregularities that would not be expected in a robust, non-simulated universe. The discovery of such anomalies could provide indirect evidence supporting the simulation hypothesis. Another method hinges on examining the computational resources required to simulate complex systems. For example, if we were able to determine the limits of computation in simulating physical interactions or cosmic events, we could explore whether the observed universe operates near these limits. The idea suggests that the simulation might manifest constraints akin to those seen in computer graphics, where limitations arise in rendering detailed environments. If we could identify such constraints at a fundamental level, it might suggest that reality is indeed simulated. Researchers are also exploring the concept of virtual reality and its implications for understanding simulations. As our own technology evolves and we create increasingly sophisticated virtual environments, studying how immersive experiences can mimic reality could provide insights into the nature of consciousness and perception. This exploration might not provide definitive evidence, but may deepen philosophical inquiries and perspectives about our existence. Finally, one intriguing proposition comes from examining the possibility of cosmic rays or high-energy particles. Some researchers suggest that if the universe is a simulation, there could be limits or specific signatures in the distribution of cosmic rays that might provide clues about its computational nature. Analyzing these particles could yield insights into whether they behave in ways that align with what would be expected from a simulated framework. While these methods may offer avenues for exploration, it's important to note that testing the simulation hypothesis presents significant philosophical and practical challenges. The fundamental nature of the hypothesis often renders it difficult to prove or disprove conclusively. Inherent within the discussion are broader questions about existence, reality, and the scope of human understanding, ultimately driving ongoing inquiry into the nature of reality itself. If we entertain the idea that the universe is a simulation, it leads to profound implications regarding the existence of a creator or designers. This hypothesis raises critical questions about the nature, intention, and capabilities of those who might have crafted the simulated reality we experience. At its core, the simulation hypothesis posits that a higher intelligence, possibly an advanced civilization, intentionally created the universe as a simulation. This would imply that the designers possess a level of technological sophistication significantly beyond our current understanding, enabling them to replicate the complex laws of physics, cosmological structures, and even the intricacies of consciousness. The existence of such creators suggests a purposeful act, which invites inquiries into their motivations and objectives for creating a simulated reality. Are they conducting experiments, creating a form of entertainment, or exploring philosophical questions about existence? Moreover, the implications extend into the nature of the creators themselves. If they designed a universe containing conscious beings capable of thought and reflection, it could indicate a desire to understand consciousness or to observe how these beings navigate the simulated environment. This would raise questions about the relationship between the creators and their creation. Are they merely detached observers, or do they interact with or influence the simulation in any meaningful way? The dynamics between the creator and the created might reflect broader themes of responsibility, moral obligations, and the nature of free will. From a philosophical standpoint, the existence of a creator or designers lends itself to a myriad of theological implications as well. It could inspire discussions about the nature of divinity, purpose, and destiny within a simulated universe. Classical questions about fate versus free will take on new dimensions as they intertwine with the notion of being part of a program versus possessing true autonomy. However, the simulation hypothesis itself does not necessitate the existence of a creator. Some variations suggest a universe that emerged spontaneously or through natural processes, akin to how our technological advancements allow us to create simulations without the need for a conscious designer. This perspective could argue that the universe functions independently of any overseeing intelligence, challenging the assumption that simulations require a deliberate creator. Ultimately, the implications of a simulated universe concerning the existence of a creator or designers are deeply philosophical, encouraging a reconsideration of existence, consciousness, and reality. Regardless of one's interpretation, these inquiries stimulate thought about the nature of intelligence, purpose, and the relationship between creator and creation, ultimately enriching the dialogue surrounding our understanding of existence. Living in a simulated universe presents profound philosophical and existential implications that challenge our understanding of reality, identity, and the nature of existence itself. Engaging with this hypothesis invites us to reevaluate fundamental concepts that underpin human thought and experience. One of the primary philosophical implications revolves around the nature of reality. If our universe is a simulation, it raises questions about what is genuine versus illusory. This could provoke a sense of skepticism similar to that articulated by philosophers like René Descartes, who queried the nature of reality and knowledge. The idea that every aspect of our existence might be engineered prompts inquiries about the validity of our experiences and the authenticity of the relationships we form. It challenges the assumption that our perceptions correspond to an objective reality, suggesting instead that we might be navigating a carefully constructed environment. Another significant implication relates to free will and moral responsibility. If we exist within a simulation designed by others, the question arises about the extent of our autonomy. Are our choices genuinely our own, or are they influenced or predetermined by the simulation's parameters? This dilemma can lead to existential anxiety as individuals grapple with the idea that their lives might be orchestrated to follow a specific narrative or purpose determined by the designers. Consequently, discussions surrounding ethics and accountability may shift, as the expectation for moral responsibility could be affected by the knowledge of being part of a preordained simulation. Additionally, the existence of a simulated universe invites explorations into the nature of consciousness. If consciousness can arise within a simulation, it prompts inquiries about the essence of being and whether consciousness is a phenomenon limited to biological organisms. This consideration could drive philosophical thought towards the idea that consciousness may be a more universal property, potentially replicated in other forms or systems, blurring the boundaries between living and artificial entities. The concept of a simulated universe also raises questions about the purpose of existence. If we are beings within a simulation, what is the ultimate aim of that simulation? Are we part of an experiment, entertainment, or a philosophical inquiry conducted by more advanced intelligences? This reflection can lead to profound existential questions regarding meaning, purpose, and our place within the larger framework of the cosmos. Lastly, contemplating the nature of our universe as a simulation can foster a sense of interconnectedness and humility, reminding us of the possible limits of our understanding. It encourages us to remain open to the mysteries of existence and recognize the intricate layers of reality that might govern our experiences. The exploration of these implications enriches not only philosophical inquiry, but also the human experience, enhancing our appreciation for the profound nature of existence itself. The anthropic principle is a fascinating philosophical and scientific consideration that attempts to explain the conditions necessary for the existence of conscious observers in the universe. It essentially posits that the universe's fundamental parameters and physical laws appear finely tuned to allow for the emergence of life and, by extension, conscious beings. This concept raises intriguing questions about the relationship between observers and the cosmos. There are several forms of the anthropic principle, each with distinct implications. The most commonly discussed are the weak anthropic principle and the strong anthropic principle. The weak anthropic principle suggests that the observed values of physical and cosmological parameters are conditioned by the requirement that they allow for our existence as conscious observers. In other words, we can only observe a universe capable of supporting life and consciousness because we are here to observe it. This principle emphasizes a kind of self-selection bias. If the circumstances were not suitable for life, we would not be here to notice them. In contrast, the strong anthropic principle asserts that these fine-tuned conditions are not merely coincidental, but rather that the universe must allow for the eventual emergence of life. This perspective implies that there is something inherent about the universe that makes the existence of observers essential. Proponents of the strong anthropic principle might argue that the universe's properties are structured in such a way that life is not just one possibility among many, but a fundamental aspect of cosmic reality. Another variant, sometimes referred to as the final anthropic principle, goes even further by positing that intelligent life will inevitably emerge in the universe and that the existence of observers is a fundamental condition for the universe itself. This principle raises philosophical questions about determinism and the ultimate purpose of the universe in relation to consciousness. Finally, the multiverse variant of the anthropic principle suggests that our universe is just one of many universes in a vast multiverse, each with different physical laws and parameters. In this view, the specific conditions that allow for life in our universe are just one realization among countless others. Here, the anthropic principle serves as an explanation for the apparent fine-tuning of our universe, indicating that while many universes may not support life, we find ourselves in one that does. The anthropic principle stimulates significant discussion across various fields, including cosmology, philosophy, and theology, as it confronts questions about the nature of existence and the universe's design. It challenges us to reflect on why the universe appears to be structured in such a way that permits conscious life and whether this reflects underlying truths about the cosmos as a whole. The concept of fine-tuning in relation to the fundamental constants and laws of physics refers to the observation that many of the universe's specific parameters appear to be precisely calibrated to allow for the emergence of life as we know it. This fine-tuning raises intriguing questions about the nature of the universe and the conditions necessary for life to exist, leading to extensive discussions in cosmology, physics, and philosophy. One prominent example of fine-tuning lies in the values of fundamental constants, such as the gravitational constant, the electromagnetic force, and the strong nuclear force. These constants dictate the behavior of natural forces and particles. For instance, if the gravitational constant were slightly weaker, stars like our Sun might not form, preventing complex planetary systems from developing. Conversely, if it were stronger, stars would burn too rapidly, again limiting the time for life to evolve. This sensitive balance highlights how even minor variations in these constants could render the universe lifeless. The structure of atomic and molecular interactions also exemplifies fine-tuning. A key example is the way carbon, a fundamental building block of life, is formed. The energy levels of carbon nuclei allow for the formation of stable carbon atoms, which can bond with a variety of other elements, facilitating the creation of complex organic molecules. If these energy levels were altered, say if the strong nuclear force was slightly different, carbon could be much less abundant or entirely absent, fundamentally changing the chemistry necessary for life. Furthermore, the expansion rate of the universe, influenced by dark energy, also appears finely tuned. If the universe had expanded too quickly after the Big Bang, galaxies would not have formed, and thus no stars or planets could arise. Conversely, a slower expansion might lead to a universe that collapses back on itself before life has the chance to emerge. The delicate balance of cosmic expansion directly affects the conditions necessary for habitable environments. And these examples lead to the question of whether the apparent fine-tuning implies some form of design or purpose in the universe. While some argue that these conditions may support the idea of a creator or a guiding hand, others suggest different explanations. The multiverse theory, for instance, postulates that numerous universes exist with varying constants. We simply inhabit one that happens to support life. This perspective proposes that while life is rare, the vastness of the multiverse could yield numerous instances of habitable environments. Ultimately, the fine-tuning of fundamental constants and laws of physics prompts profound inquiries into the nature of reality and existence. Whether seen as evidence of design, a product of chance, or manifestations of a broader multiverse, these discussions continue to shape our understanding of the universe and the conditions necessary for life. The apparent fine-tuning of the universe is a compelling topic that suggests a potential explanation involving the concept of a multiverse. This multiverse theory posits that our universe is just one of many universes, each with different physical laws, fundamental constants, and conditions. The idea that our universe appears finely tuned for life could be understood within the context of a multiverse, as it provides a framework that addresses the question of why we find ourselves in such a unique and life-supporting environment. In a multiverse scenario, it is proposed that there are countless universes, each formed with varying parameters. Some of these universes may have conditions that support life, while others may be inhospitable, lacking in the necessary physical laws or constants for life as we know it. If this idea holds true, the fine-tuning we observe in our universe could be simply a result of chance. We reside in one of the rare universes where the parameters happen to align in a way that permits the emergence of conscious beings. This notion dramatically reduces the improbability of finding a life-supporting universe, as there would be countless other universes that could harbor vastly different characteristics. Moreover, the multiverse theory aligns with certain aspects of modern physics, particularly the inflationary model of the early universe. This model suggests that the rapid expansion of space after the Big Bang could lead to pocket or bubble universes, each with its specific properties and constants. These bubbles might be generated through a myriad of quantum processes, resulting in diverse and distinct universes with variations in fundamental constants. However, while the multiverse theory offers a compelling explanation for fine-tuning, it remains an area of active debate and speculation. Critics of the multiverse hypothesis argue that it challenges the scientific commitment to observable evidence, since many of these alternative universes may be inherently unobservable or inaccessible to us. Moreover, the multiverse's implications raise philosophical questions regarding the nature of scientific inquiry and the definition of reality itself. The apparent fine-tuning of the universe could indeed be interpreted as evidence in favor of the multiverse theory. This hypothesis provides a potentially satisfying explanation for the peculiar conditions we observe, framing our universe as one of many possible realms. Nonetheless, the nature of fine-tuning, the validity of the multiverse concept, and their implications for understanding existence continue to stimulate significant discussion among scientists and philosophers alike. The anthropic principle has significant implications for discussions about the existence of a creator or designer, as it intertwines scientific observations about the universe with philosophical and theological questions. This principle highlights the fine-tuning of the universe's fundamental constants and laws, suggesting that these parameters must fall within specific ranges to allow for the emergence of conscious observers like humans. The implications can be explored through various lenses. One interpretation is that the intricate calibration observed in the universe may point toward the existence of a creator or intelligent designer. The strong anthropic principle, in particular, implies that the conditions necessary for life are not merely coincidental, but are somehow aligned with the emergence of conscious beings. This alignment might suggest a purposeful act by a creator who set the parameters of the universe intentionally, leading to the existence of life and consciousness as we know it. In this context, the anthropic principle could be seen as supporting theistic or deistic viewpoints, positing that a higher intelligence intentionally designed or fine-tuned the universe for specific outcomes. Conversely, another interpretation of the anthropic principle, particularly the weak anthropic principle, emphasizes that we can only observe a universe conducive to life because we exist as part of it. This perspective suggests that the universe's parameters must allow for observers, but this does not necessarily imply design or intention. Instead, it can be viewed as a self-selection bias, where the existence of observers informs the understanding of their environment. This interpretation of the anthropic principle may not support the notion of a creator, but instead encourage various alternative explanations, such as the multiverse theory, indicating that our universe is one among countless others, each with different conditions. Additionally, the implications of the anthropic principle raise important philosophical questions about purpose and meaning. If we accept that the universe exhibits fine-tuning that allows for conscious life, it prompts deeper inquiry into the purpose of existence. Is the remarkable nature of our universe meant to convey significance or meaning? And does that align with the idea of an intentional creator? Ultimately, the anthropic principle serves as a bridge between empirical observations in cosmology and the broader philosophical and theological discussions regarding existence. While it can lend support to the idea of a creator or designer, it also opens the door to alternative explanations that challenge traditional viewpoints. As humanity continues to explore our universe and seek answers to fundamental questions, the implications of the anthropic principle continue to inspire significant discussions about existence, purpose, and the nature of reality. The anthropic principle significantly influences our understanding of our place in the universe, prompting introspection about existence, meaning, and the conditions that allow for conscious thought. By highlighting the apparent fine-tuning of the universe's fundamental constants and laws, the anthropic principle encourages us to reflect on the relationship between human beings and the cosmos. One of the primary influences of the anthropic principle is the sense of connection between our existence and the broader universe. It suggests that the universe is not random or arbitrary. Rather, the specific conditions that allow life to flourish are intricately tied to the very nature of reality. This brings forth a recognition that our ability to ponder and observe the universe is not merely coincidence, but is linked to cosmic parameters finely tuned for life. Such a framework can inspire a sense of wonder and appreciation for both the cosmos and our role within it. Moreover, the principle encourages a reconsideration of significance and meaning in our existence. If the universe is tailored for conscious observers, questions arise about the purpose behind such design. Are we here for a specific reason, or does our presence in an accommodating universe highlight the mere possibility of conscious beings arising in such conditions? This line of inquiry can have profound implications on philosophical thought, shaping various views about existence, purpose, and destiny. The anthropic principle also nudges humanity toward a greater responsibility towards sustaining life. Recognizing that our survival depends on a finely tuned environment can foster a sense of stewardship. This awareness can influence how we approach issues such as environmental conservation and our treatment of the planet as we grapple with the implications of living in a universe that has, against immense odds, allowed us to exist and thrive. Conversely, the principle can also incite existential inquiry concerning humanity's limitations. It serves as a reminder that, while we are capable of great intellectual and technological achievements, our understanding of the universe remains contingent upon parameters that could easily be different. This realization can cultivate humility, encouraging a recognition of the fragility of life and the intricate balance of forces that allow for our existence. The anthropic principle profoundly influences our understanding of our place in the universe. It intertwines insights about the nature of existence, purpose, and responsibility, allowing us to appreciate the intricate connection between conscious observers and the universe's remarkable and accommodating conditions. As we reflect on these implications, we are inspired to explore further the mysteries of existence, prompting both scientific inquiry and philosophical contemplation about our ultimate role within the cosmic tapestry. As we conclude our journey through the unexplained mysteries of the universe, we find ourselves both humbled and inspired by the vastness and complexity of the cosmos. We've explored questions that have puzzled humanity for centuries, and we've glimpsed the cutting-edge science that is bringing us closer to the answers. But in many ways, our journey has only just begun. With each new discovery, we unlock new mysteries, and with each answered question, we uncover deeper ones. The universe, it seems, is not in the habit of giving up its secrets easily. And yet, that is precisely what makes this endeavor so exciting. As we continue to probe the depths of the cosmos, we push the boundaries of human understanding, and we expand the frontiers of what is possible. We learn to see the universe not just as a collection of stars and galaxies, but as a grand and intricate puzzle waiting to be solved. So while we may never have all the answers, we can take solace in the fact that the pursuit of knowledge is a noble and worthwhile endeavor. And as we look to the future, we can only imagine what new wonders and mysteries await us. Perhaps someday we will unravel the secrets of dark matter and dark energy. Perhaps we will discover life on distant worlds or learn to navigate the strange realm of quantum physics. Or perhaps we will simply learn to ask better questions and to see the universe with new eyes. Whatever the future holds, one thing is certain: the mysteries of the universe will continue to beckon us, to inspire us, and to fill us with a sense of awe and wonder. And as long as we keep exploring, keep questioning, and keep reaching for the stars, we can be sure that the journey will be worth it.